Anand, can you see me? Yeah.
Yeah. Am I audible?
Yes, you're audible.
I'm great.
So, yep, we are back like half an hour.
Yeah.
So, half an hour of rest that we get, yes, from the break. So, yes, now we have like the man himself. Like we know him, like from lot many of his contributions, Mr. Rajiv, sir. So, yeah, so he's there with us. Hi, sir. Can you hear us?
Hi, yeah. Can you hear me okay?
Yes, so glad to have you with us, and
Okay,
it's
thank you.
complete honor, honor to us. And yes, so Arnab, just like if you want to give a
Yeah.
brief introduction about, so please do that.
Yeah. So, welcome to the conference, Rajiv sir. Could you just tell us about a bit about yourself? Like, how did you just got started in the industry, and what are your learnings? Before we just move on to the topic.
Sure. So I assume we are live, yeah?
Right. Yes.
Yeah.
Okay. Yeah, so thank you to Razor and to the rest of your team for having me. And I'm Rajiv. I am the founder and the organizer of Securium. So for my introduction, I've been doing research in security for a long time now. Started in the traditional Web 2 space, looking at application security, doing some research over there in the software security space, and then went deep down the stack all the way to the OS as well as hardware security. So this was over 7 years, and then my introduction to blockchain and specifically Ethereum was around the maybe around the pre-ICO craze, around 2016, 2017-ish. So that's when I got introduced to Ethereum, to smart contracts, and given my background in security, smart contract security made a lot of sense. So that got me interested into the space. And where I really got my hands dirty, where I really sort of uh, dive deep into the smart contract, just understanding the space, understanding Solidity, all the security stuff was during my stint with Trail of Bits, which is, as some of you may know, it's one of the leading companies, audit firms in this space with many tools. So while I was working with Trail of Bits, I had an opportunity to contribute to their Slither tool, which is, I would say, which is a widely used static analysis tool that many developers use, Solidity developers use for security, right, for spotting basic security issues. So that was my introduction to smart contract security. And then fast forward to last year is when I started this effort around Securium, and I can talk more about it. But yeah, so that's sort of my background.
Rachel, your mic is muted, I guess.
Yes, yeah. So like I'm a little bit dumb. So yeah, I got it. So yeah, I was just saying that thank you so much for all the contributions that you have made for the community, for all of us. Like whether it is Slither is there, the well-known and very famous the boot camp provided by Securium, and yeah, so it has actually helped a lot of us, and the content is actually still helping a lot of us. And to the guys who are looking forward to join this Web3 security space, they are like the first step that we recommend those people to just go ahead and fresh up their minds on the other resources provided by Securium Bootcamp, like because those are like one of the well written sorry resources available. So yeah, with that, we'll just keep our mouth shut and give the stage to you. And the stage is all yours, sir. Please share your insights.
Sure. Thank you for the kind words, Razor. So shall I go ahead and share my presentation? Let's see how that
Yes.
works. Okay. All right. Do you guys see the first slide?
Yeah, the slide is clearly
Yeah.
visible. Yeah, perfect.
Okay. All right. Thank you. So let me start with a disclaimer, maybe two disclaimers, that this is going to be a short presentation. I would like to leave a lot of room for any questions that we may have. Happy to have a discussion with Razor and with Arun as well. So that is one. And the second disclaimer is that unlike some of the, well, most of the other presentations, other talks you may have heard during this Unchained event, this my talk, is going to be non-technical. I'm going to be talking about Securium. I'm going to be talking about scaling security and some of the efforts around that we are trying to do as a community in Securium. Yeah. So Securium, as you know, as you can see, is very simply put, it's security plus Ethereum. And the idea there is that the entire focus is on the security aspects of Ethereum, right? And so far, all of this, most of this has been in the application security space. So smart contracts, we haven't really had a chance to go deeper down into some of the more protocol specific aspects or some of the infrastructure and other. I mean, there are so many aspects to the security of Ethereum, right? So that is sort of the origin of Securium. And just to sort of give a bit of context and backstory to Securium, as with many projects, Securium started as a side project roughly about a year ago, Jan of 21. It started as a newsletter while I was still working with Eat Status. So I just started writing. I mean, this is, you see a lot of security researchers doing this, is to write and share their research, their learnings with the community, right? So it's in many ways peer-to-peer, even from that perspective. So I wanted to do a similar thing. So I started writing a weekly newsletter on Substack. And I started off with sort of perspectives on Web3 security, trying to just share my thoughts on what or how Web3 security is different, at least my perspectives on how it is different from the Web2 security space that's obviously been around for, well, as long as computing has existed, right? So did a bit of that, looked into ETH2 as it was called back then, started looking at some of the protocol exploits and the reasons behind that. So did that for maybe about 10 10 weekly newsletters for around 10 weeks. And then realized that there is much more that can be done, that needs to be done in this space. And this was really around building a community, building a lot more educational content, building a structured approach to a lot of us who wanted to get into this space, who may have been researchers, been building products and services in the Web2 space, in the traditional internet, AppSec, pen testing, what have you, right? All these aspects. And for all of us who wanted to jump into the security, well, the Ethereum security space or smart contract security space, there is a lot of content available. And a lot of this is really from the various smart contract auditing firms, be it TraderBits, be it Consensus Diligence, Open Zeppelin, all these teams in their spare time, right, have been sharing a lot of the research and thoughts and ideas and best practices that they've been using to improve the security of this space. So all this existed, but there wasn't really a structured approach, right? So when somebody, even like me, wanted to get into the space, you would, this was back in 2016, 17. I don't think there were so many Telegram channels or Discords yet. So you would look up and you would read up the solidity documentation, you would look up the white paper, yellow paper, you would join a couple of these channels, be it Reddits or Jitters, and look at GitHubs, look at the EIPs, look at ERCs, look at the Open Zeppelin libraries, whatever existed back then, look at the Solidity compiler and the various the evolutions, the revisions of that, right? So all that was good, but we're all sort of used to structured approaches, be it in schools, be it in colleges, universities, or online courses or wherever, right? So something structured, something more definitive always helps. So that was sort of the motivation behind Securium and behind the concept of a bootcamp, right? And this wasn't new. I mean, the problem was well known that there is content and there is a lot of demand, but nobody was really doing it, right? I mean, they were doing it. I think there were a couple of efforts, very sincere efforts that were being done. One of the big ones that I was aware of, I was part of, was the Gitcoin Kernel initiative that I'm sure many of you are aware of, maybe have been part of as well, right? So they have this concept of kernel blocks. So back then, I think it was kernel block 3, and there were multiple tracks. There was a security track. Corey Petty from Status was heading up the security track, and I was at Status, so I was helping him sort of work with that community and talk to them and sort of build material and organize an effort around it. So that was sort of, again, a backstory to the motivation, but that was more generic, right? It wasn't only smart contract security or only Ethereum smart contract security. So my motivation there was that there is so much that can be done just focusing on Ethereum smart contract security and not for now worry about other chains or other layers of the stack and so on. So that was really the motivation, and someone proposed that if I was really serious about this, then I should I should really experiment with this approach. So that's what I did, and I'll talk a bit more about the boot camp in a few minutes. But the main motivation around the boot camp was really this aspect, right? So for I'm sure everyone who's dialed into this event is aware of this meme, right? The UAP meme. And what this really signifies is the state of security, the state of smart contract security in the Web3 space. I mean, there's nothing, it's not even specific to Ethereum, it's not specific to smart contract, it's really all over the place, right? What this indicates is, at least to me, is that there is a lot of this happening, right? It's very common. I mean, if you're on some of the widely known Telegram channels or Discords that work on Ethereum Ethereum security, then you are probably familiar with this, right? The frequency of this is really, really high. Maybe not every day, but there's at least once a week, and depending on what bar there is, if it is a $1 million hack, maybe nobody even notices that, depending on what chain it is, what protocol it is. But this is very common. Protocols, there are many, many vulnerabilities, unfortunately, in the various protocols deployed on the blockchains, and many of them get exploited, right, over time. And this, unlike the Web2 space, the impact here is immediate and it is tangible, right? And people here may obviously be aware of this, but what that means is that unlike in the Web2 space, it is not simply a password database dump or a denial of service, or let's say the extreme cases of ransomware. where the impact is sort of delayed, right? It may be immediate to some extent, but it's not immediately felt by the end users in many cases. And there is a way to sort of address that by the authorities that are responsible for the security. So in this case, in the Web3 securities case, or in the smart contract security case, the tokens, the Ether, or whatever we are talking about that is being managed by the smart contracts, when they are exploited, they are lost to the attacker, to their addresses immediately, and in many cases irreversibly, right? So unless we get into specifics of, well, these tokens went into some centralized exchanges or certain tokens that could be and addresses that could be blacklisted, right? So without going deeper into those details, if you zoom up, the idea here is that the state of security is still very bleak, and there are many reasons for that. It's not like nobody's doing anything about it. We are really very early in this space. Ethereum itself is less than, well, it is around 7 years, into this. Into the deployment, and the blockchain space as such, even if you go all the way to Bitcoin, it's just over a decade old, right? So when you contrast it to the Web2 space, to the web space, to the internet, right, that we have known and that we use, that is, we're looking at decades of work, right? All the way from the 1950s and 60s and 70s with the ARPANET and with all the languages, with the web. So we've had a lot of time to actually get to where we are in the Web2 space, and the picture there isn't rosy either, right? The state there is, well, as we know, it's still it's very comparable to where we are in the Web3 space. So there are many differences. I talk a bit more about this in one of the articles that I've written. But the key point here is that this is not just a meme. It's very real, and there are many fantastic researchers, white hats. Many of them presenting at this event, many of them hosting this event, many of them listening to this event, who are trying to help better the security here, right? So what's the point of all this, right? The point here is that a lot of the security techniques, right, are mostly manual. Because if things were completely automated, if you had automated tools that could prevent bugs from getting to smart contracts, that could detect bugs in smart contracts, that could monitor deployed smart contracts and prevent any attacks on them, prevent the exploits. If that were to be the case, then then it would just be a matter of adoption of those tools and techniques, right? But unfortunately, we're not there yet. So again, many reasons for that. The one big reason is, like I said, we're very early in this space. We have many tools and techniques being developed. The commonly used tools in this space that you would come across from a security perspective are Slither, Echidna, Mythex, Mithril, the Certoras prover tool, SFT checker, the Solidity compiler itself that has a lot of these things built in. Then you have a variety of Open Zeppelin smart contracts that have been community vetted, audited, that have raised the bar. You have, like I said, the compiler itself, where many security checks are now built in. The most famous one being the bound checks that got into the Solidity compiler 0.8 and above. So all these things are happening, but yet the security, a vast majority of the security exploits, security vulnerabilities, tools, if you go down that stack, right, or if you go in that flow, they're still mostly manual. And the reason for this is, there are many reasons, but one big reason is something that is fundamental to how programming works itself, something based on how humans interact with tools. So you obviously need humans. We are the ones building out the protocols, right? Be it the DeFi protocols, NFT, DAOs, whatever it is, right? So that's one aspect. Then humans obviously are the ones building out the tools, be it the compilers, be it the slithers, be it the IDEs, be it the hard hats, right? Or be it the monitoring tools, be it the bug bounty platforms. All these are being built by humans. We haven't got into a point where we have AI based techniques for automatically building these tools yet. So that being the point, from a philosophical perspective, humans are error prone for various reasons, and errors creep into all aspects of all aspects of the cycle that I just talked about. So obviously, errors creep into smart contracts. Even the most well-intentioned, security-minded developers do introduce bugs unknowingly. Let's ignore all the intentional bugs and the rugs for now, right? So if you look at security-conscious developers who are using the state-of-the-art tools, the complexity, the state of the stack, and when I say the state of the stack, I mean the Ethereum protocol itself is evolving. We have a big merge coming up. We have the compiler evolving at warp speed, really, and for the right reasons, right? New features are being introduced, security and otherwise. Then we have the applications itself that are exploring several dimensions, be it various DeFi protocols, NFTs, DAOs. I mean, those are the names that often come up, but there are so many different applications, and a lot of these are because of how or the philosophical aspect behind the blockchain, definitely behind Ethereum, is the permissionless, borderless, open paradigm, right? So anyone, anywhere can actually build and deploy onto the blockchain without being restricted by an app store, or without being restricted by the device they're on, or without being restricted by really anything else, really, right? So all these things really contribute to the vulnerabilities and the exploits creeping in. And one big reason why a lot of these techniques are still manual is that a lot of the things that can be automated are being automated, right? So if you focus specifically on the bug detecting tools, right, the scanners, the linters, and the static analysis, formal verification tools, it's still humans who have to codify whatever they know about the security properties and build them into the rules that can be checked, right? So those can be done. And those rules obviously are as good as the humans who actually constructed those tools, wrote the specifications, got the requirements, converted them into the rules, be it properties or anything else really. But those rules can be done generically across smart contracts. Let's say, focusing on Solidity, what we can write those rules for Solidity, right? With respect to Solidity and with respect to the EVM, right? So all these aspects of reentrancy, bound checks, modifiers, anything that can be codified at this level of the stack can be codified and will be codified, has been codified if you look at Slither and all these other tools, right? Now, what cannot be generically codified is all the things that are application logic specific. And that forms a bulk of the issues that we are seeing today, right? So that aspect of application logic, and that sort of includes the economic vulnerabilities as well. So those are very specific to the application, to the smart contract, and those are really particular to the specification design and the implementation of that particular project or that particular application. So a generic tool such as Slither or any, whatever your favorite tool is in this space, cannot sort of generalize that rule without knowing what that application logic is, right? So that's sort of inherently the definition of application logic. And that, and this is nothing new to the Web3 space. This is obviously a problem in the Web2 space. If you look at any software application, there's only, so many rules that can be generic across the applications, across the OS, across the browser plugins or anything that you're looking at, right? So this manual process means that we need, obviously more people, right? We need more humans to write these rules, to run these tools, and to do everything really in this space, right? So that is great. So that's really a motivation. So that's good, right? I mean, especially for all the security folks, it means that there is a lot of demand in the security space. It has been so for the last 2-3 decades, and definitely so in the Web3 space for the last several years now, right? And it's only building up, right? I mean, the demand is only building up. Now, that's great. So, if you look at basic economics, if there is a high demand, then supply should match the demand, which means that there should be a good supply of people who understand what the issues are. Now, that is the problem, right? So in this case, the demand obviously for people who have knowledge of Ethereum, not just Ethereum, not just developers, right? You need to have a security mindset. So that is something that is not that can't be turned on by the flip of a switch. It needs to be learned. You need to understand what a trust model is. You need to understand what a threat model is. You need to understand security has been around ever since computing. Well, even before that, right? If you look at cryptography, you can go like centuries ago, and all these things really existed, right? So you need to understand a lot of that and more when you look at the Web3 space, right? So that is not an easy thing to do, and that is sort of what leads us to where we are, which is the unsustainable security pyramid, as I look at it, right? So we have Ethereum, and then we have billions of dollars of value, right? I mean, if you look at Ether's value and you look at all the protocols and their tokens on Ethereum, you look at all the stable coins on Ethereum, and really, I mean, the whole ecosystem that way is sort of connected, right? With even other blockchains, we have bridges. So things are not isolated, not siloed as we may think, right? So when you have all these billions of dollars of value in thousands of protocols, and unfortunately, the security of all that value and protocols is being shouldered by really hundreds of experts, right? And this is, this is probably being generous. So people have actually tried to look at or try to identify, okay, how many people understand Ethereum security. And even if you go by very simple metrics, such as, okay, let's look at all the people interested in Ethereum security. So if you take the most popular Discords or Telegram channels, there are maybe 1,000 people, right? Like Securium Discord, I think, has maybe 2,500 people, right? So these are all the people. I'm not claiming that everyone who knows or interested is on these channels, but this is a rough metric, right? So we have thousands of people interested, and maybe hundreds of people who have been looking at this for more than several months now. And this clearly, right, even if you do the basic math, this clearly is not sustainable, right? So that is the problem. That is really the motivation. I mean, this is a challenge, but there's also an opportunity for all of us here to actually fill this gap and to make, to increase the level of education, to build the community out so that there are more people who can really address the demand. And this demand is unlikely to reduce, right? It's only going to increase multifold by orders. So that's what we are looking at. And if you combine this with sort of the manual aspect that we talked about, right? How it's still a lot of human effort, then it means that right now we need to train many people, right? We need to train ourselves, and nobody's an expert in this space. We're all students. Things are evolving at such a speed that if you take a break of a weekend or a week or a month, you're really already out of touch with all the latest exploits that happen. You maybe missed out a couple of versions of Solidity, a couple of the latest libraries or the latest tools and the protocols. So things would have moved. So there is, we all of us need to be really running on the treadmill to be where we are, and we need to get more people onto this treadmill of Ethereum security, right? So this is really sort of the first mission of Securium, and let me jump on to the bootcamp part, right? So this is where this is where Securium's initial effort started and is headed. So Securium's boot camp, Epoch Zero, happened in the second half of last year. And this was made possible thanks to a generous grant from the Ethereum Foundation and to 3 sponsor partners, Consensus Diligence, Sigma Prime, TrailerBits, all of whom are leading security firms in the Ethereum security space, smart contract security space, auditing space, what have you. Right? So that is what made it possible. And what really happened during the bootcamp was that a lot of the content that Razor was referring to earlier was really curated content, right? There was maybe 20% of the content that I sort of contributed, but a lot of it was really curation of content that existed from the likes of, again, the people that you see here, right? The teams that you see here. TrailerBits, Slither tool has a lot of these rules codified. They have a lot of good documentation, diligence, and really Open Zeppelin, all the fantastic teams that are driving, that are raising the bar in the space. They have fantastic documentation. Now, what I did was to really curate it and make it more structured in a way that I thought would be helpful to myself and to others, hopefully. So that was sort of the motivation, and that is what resulted in this bootcamp, the content for the bootcamp, which is still being used. So we had 3 months of the bootcamp. The first 2 months were 8 weeks of structured effort, where the first week was really learning everything about Ethereum, compressed in 1 week. Then Solidity 101, Solidity 201 was really learning every line of documentation from the Solidity docs, right? And Open Zeppelin, all their libraries that are really used by every project today, right? So that was that formed the base layer, if you will. And then was really the security pitfalls and best practices. So that took all the participants through really all the curated content that talked about all basic pitfalls and best practices. There are about 200 of them, and this is just one checklist. There are many checklists, so this was just sort of as a table stakes that everyone needs to understand, but people are always welcome to add more to this to learn all the other checklists as well, right? So this was sort of the process, and then finally, in the last 2 weeks of the first part of the boot camp, we all looked at the audit findings. So audit reports, as we all know, are a fantastic source of learning, of real-world protocols, of things that could have gone wrong but were caught by the audit teams. So that was what happened. And in that learn phase, every phase, obviously, we need to have an assessment. So we had 8 quizzes, timed quizzes. So that, that was sort of to assess the participants. And the reason for that was that the final stage of the bootcamp, the last month in December, we had 4 protocols that came in for a security review. Right, so the ones listed here: Primitive, Sherlock, Sushi, and Tracer. So participants went through that. So I believe it was a good experience for many of us. Obviously, there were things that could have been done better. A lot of learnings. We had about 650 participants who started off with the first quiz, and finally about 250 of them finished taking all the quizzes, right? So all these participants will be given NFT badges to sort of build their reputation, to showcase that they did indeed put that effort and got a particular score in the quiz or in the review, right? So that was Bootcamp Epoch Zero. And what we are doing now is using the learnings from Epoch Zero, we sort of jumped through all the other numbers and we straight away went to Epoch Infinity. And the reason for that is that it didn't feel like a 3-month or a 1-month sort of a discrete bootcamp made sense in the crypto world, right? We wanted participants to join whenever they want, wherever they are. And by the way, the bootcamp is completely async. Securium completely runs on the Discord. The website is unfortunately outdated. So if you are looking for Securium, then please do join the Discord. That's where all the announcements are made, right, with respect to the bootcamp. So Bootcamp Epoch Infinity, and I realized that I think already out of time, so I'm going to be stopping in a minute. Bootcamp Epoch Infinity is structured as an infinite series of races and cares, right? What you see on the slide, right-hand side of the slide here. So race is just a catch-all term for a quiz. It could be a challenge of any sort. It could be a CTF or anything else in the future. But that is really what is used as an assessment for the participants to see if the participants understand Solidity, Ethereum, smart contract security, right? So participants are welcome to join the Discord at any point. They're welcome to look at all the content that has already been created and curated from Box Zero. It's all there on Substack, it's on YouTube, and they're welcome. I mean, they're encouraged to look at external content, be it be it from the Discord here, be it from UnChained, be it from Open Zeppelin, be it from Immunify, any of the fantastic teams that are trying to raise the bar here, right? So read at your own pace whenever you want, and when you're ready to, when you feel ready, then register using a Google form to participate in the race. And there is one race, at least one race that happens every month. We had the first race happen in Feb. There's one more that is going to be announced in March, first week of March. So people take this. This is again a very short, it's like a 16-minute multiple choice quiz that really tests if people understand the basics of Solidity, basics of Ethereum, basics of smart contract security. And the top participants, this is obviously scored, the top participants in the race are invited for the various cares. And CARE here stands for Comprehensive Audit Readiness Evaluation. So it's another term for a security review, but it's not an audit. It happens before an audit. It's really audit readiness. So all the learnings from the various checklists that participants have understood, they apply those on the protocol that comes in, that collaborates with Securium in that 1 week, right? So it's a 1 week effort. And as you see, we've been collaborating with multiple partners, and all these have happened just in the 1 or 2 months, right? So in Jan, Feb, and March. As an example, Badger DAO, the protocol is going to come in for a week of care in the first week of March, right? So people, the top participants in a race in Feb will be invited to participate in that care. So they do the security review, they discuss, collaborate, and they write up a report. And at the end of 1 week, they submit the report, right? And then Securium compiles, curates, right, all the valid findings from those reports and provides that to the protocol, right? So the protocol is benefited because this is an audit readiness, and it really helps them move security, it helps them shift left to security, right? So they are better prepared when they go for an audit that is 3 months or 6 months down the road, ideally as close to the audit as possible. And the auditing team is happy because they are getting more mature protocol code that has been sort of cleaned up of all the low-hanging security pitfalls and best practices have been implemented, right? So that the audit team can actually use their valuable time in diving deep into the manual analysis, into the application logic, use the formal verification tools. All that requires a lot of effort. Now, they don't have to worry about any of the low-hanging, basic pitfalls that should ideally have been fixed earlier on. So that's what CARE is about. And CARE X is really a customized care engagement that Securium is working with multiple partners. So right now we are working with Spearbit, with Sherlock. So Sherlock we had a capture the flag, which was very interesting. Can talk more about it later if you have time. We're also doing one with Certora, which is really a 5-week effort where the participants are being trained with the prover technology. And obviously the incentives are the NFT badges, but then some of these collaborators also have incentives, financial incentives. Some of them are, all of them are really looking to hire a lot of these participants because they've been trained, they have shown that they have performed really well in the races, they have cared for the protocol, or they've done the CTF or any of those things, right? So those are the various things that are going on with the Securium Bootcamp. And I will stop there with that. And on another interesting note, Securium is also, besides the bootcamp, we're also trying to get the community around Ethereum, around the Ethereum security ecosystem. So there is a TrustX event. This is the first in-person event that Securium is hosting and organizing in Amsterdam as part of the broader Dev Connect event. Would love to see a lot of the people here join us at that event. Again, this will be live streamed for free, and in-person attendance. The details will be shared soon. So with that, let me stop. I don't know if I have any more time, but thank you.
Yes. So, yep. Once again, it was a wonderful talk, and yes, very cool insights that we have got from your talk, and the things that have been done via Securium Bootcamp, that we can say, right? There was the bootcamp itself, there was the races itself, the care protocols, like the protocol that was selected for the CareX reviews and all. So all of these actually build a methodology, a mindset for our enthusiasts that is actually looking forward to join the Web3 space. So just as a recap, if I have to recommend a step-by-step like approach that one should be following to get into the security space, is get some organized knowledge from the Securium Bootcamp itself. Participate in the care, like the races that we have in the bootcamp itself, and follow some CDFs, right? And right, maybe reading some reports from the auditing firms that we have, like Trail of Bits, Consensus, from us as well, QuillAudits. So we do audit as well, and we are doing like back from back in 2018. So yep, so reading reports as well, that adds to our skill factor. So anything else that you want to add into it, sir, would be great.
No, I can go on talking about this topic, which
Yes,
is
right.
for forever. But
Mhm,
yeah, I would be happy to take any other questions.
mhm,
So I would just like to say that thank you for
mhm,
inviting Securium to this forum, to the Unchained event. I
mhm.
do see some comments on the restream here. Thank
Yes.
you for the kind words. But yeah, if there are any other questions? There are many, many fantastic teams,
Mhm,
many different forums, be it Code Arena, be it Unify, be it Quill, be it RazzorSec, be it
mhm,
Eat Security. So we just need many, many more such. Well, I would say many forums. We need more people to
mhm,
join us. We need to train ourselves better. We need to, because there is a lot of, unlike the Web2 space, there's obviously a lot of things at stake, right? So, especially on the security reviews in particular. So, if a security review doesn't really do justice to the protocol, and if the protocol is relying, on the security review, then things can go wrong, and obviously fingers are pointed. Um, I think, as a community, we just need to be very careful about how we position things. We need to make sure that everyone understands that security, there is no perfect security, there's no absolute security. Even if a protocol goes through multiple audits, there could be things that could be missed. Even if they do formal verification, things could be missed. So all these caveats, all these disclaimers need to be explained, right? Need to be educated. So yeah, I think there's a lot of work ahead. We need more people, and
right.
look forward to everyone joining.
Yep. Yes, that is obviously true. And yes, with that, we would like to say thank you, like once again, for being a part of Unchained. And like it was a pleasure on us to have you with us. And yes, we are receiving a lot of appreciation, like regarding the boot camp itself and regarding the contribution that you have made. So yep, from all of our side, we are just wishing best of luck for the boot camp and to like contribute more to the community. And yes, we are looking forward to see you soon, sir. Have a nice day. Take care.
Thank you.
Right. All right, Arnim. So I guess we
Yeah.
are a couple of minutes late, I guess, but
Yes.
that's fine because we are just learning things and getting insights from the man himself, Mr. Rajiv sir. He has done a lot of contributions. And next we have on call. I can say he like I don't have actually the points that I can say because he has literally contributed in every possible domain that you can think about. Please have him on the call.
Yeah. So we have Gogol sir. I mean, he's just like pro in everything.
Hi
Like,
sir, how are you? Sir, I guess you're on mute.
yeah.
Hey, Arinim Tejaswa. Hello.
Yeah.
Hey.
Yes sir, you are visible and looking really fine.
Yeah.
Yes. So I was just introducing about you, like you name a domain, he has possibly done a contribution in that, like talking about machine learning, talking about blockchain development, security, AI, ML, pick anyone you want, and he has done a lot of work. So I just want to first appreciate for all the contributions that he's constantly doing for all of us and for all the community, that because we actually need that, right? We actually need all of the leaders actually come forward and help us, because this kind of information is needed on a daily basis. Like if these researchers, if these security researchers won't be sharing their valuable research with us, we won't be learning new concepts and won't be growing up in this field. So once again, welcome to Unchained 2022, sir. And it's the next second year, and I
Yeah.
hope things are going fine at your end. And yeah,
Absolutely.
adding on to it, like he's my research partner as well. So we have done a lot of research together and talked in many of the conferences. So yeah, you possibly have seen us together on many of the talks together. So yeah, so with that, I won't be taking much of your time, sir. The stage is all yours.
Thank you.
And yes, just rock it.
Thank you so much, Tejaswa and Arinim. I am really happy to see the second edition of Unchained in 2022 coming. I mean, we have a lot of global experts on blockchain security, and great to know about Securium event. So, without further delay, let me start sharing my screen and take you to the presentation. If there is a delay in the delivery of content, I'll switch off my camera.
Okay. Arnhem, can you just change the overlay?
I'm just sharing my screen.
Okay.
Are you able to see my screen?
Yes, we can see it now.
Okay,
Perfect.
great. So we are learning, we are going through the Hyperledger Fabric, one of the early block permission blockchain platforms, which started as early as December 2015. So Hyperledger Fabric. Why I've chosen Hyperledger Fabric is the way Hyperledger Fabric is engineered is very different from quite a lot of our open blockchain platforms in which I was working in the last few years, be it Ethereum, Polkadot, Cosmos. or Algorand or Eternity, their model, be it the model about the identity, and be it about the identity and access management, or be all about consensus, everything is done in a very different manner. And interestingly, like when you look at people who are trying to deploy blockchain first time in their enterprises, many of them are choosing Hyperledger Fabric. And since the smart contracts in Hyperledger Fabric is written in language, general purpose languages like Go, JavaScript, and Java, quite a lot of time the developer community is not very much aware of the issues or security challenges that can creep in Hyperledger Fabric based systems. So there would be a perception that since this is a permission system, it's a system with a lot of standard security modules, we don't need to worry much about security. But that's besides the point. We in this session we'll be going through some of the key concepts, key components of Hyperledger Fabric, and how security challenges in these components need to be addressed. So, Fabric is a permission system. The identities are registered through a module called Membership Service Provider, and identities of participating nodes are again maintained by Membership Service Provider. For managing consensus, there is a particular module known as Ordering Service Node. Membership provider is one of the very critical component in the platform. It manages access by issuing credentials in the form of cryptographic certificates for authentication and authorization. This project started in December 2015. With the guidance and the leadership from Linux Foundation and 30 companies to set up a project to promote cross-industry blockchain technology collaboration. From that 2015 onwards, it has grown phenomenally, and it has grown in like both in depth and in breadth. We could say the next diagram will show you how versatile this Hyperledger project ecosystem right now. In this Hyperledger project community, the first one, we could say first Fabric, Iroha were one of the early protocols, and then came Hyperledger, Baru, Sawtooth, Indy, Grid, and thereafter projects like Ares, Caliper, Cello, Explorer, Quilt, and Ursa. The interesting about the Hyperledger project ecosystem is many of them are interlinked or could be used in integration. For example, Hyperledger Caliper can be used to measure the performance of Hyperledger Fabric. Hyperledger Ursa can be used to add custom cryptographic libraries for digital signatures or zero knowledge proofs in Fabric and Indy. And Hyperledger, recently there is a new interesting project called Besu, which is doing a significant contribution towards the interoperability between Ethereum and Hyperledger Fabric. And Ares is a kind of a client which works very well with Indy. So let's now get into Hyperledger Fabric, as it is the focus of this discussion session today. This reference architecture diagram shows various components of Hyperledger Fabric, ranging from identity to identity, like we mentioned earlier. Membership service provider is a very crucial component in the identity, and it is very important since we are dealing with a permission system. So enrollment of credentials, or the attribute based authentication, all this is done through membership service provider. Then comes another set of modules for the ledger, the core ledger where the blockchain is generated. So the ledger consists of networking component and distributed system component. And also, then there is another core module related to transactions. How do you get the transactions from decentralized applications and clients? So the transactions are ordered and validated. That life cycle, how the transactions are uh, executed, ordered, and validated. That's quite different from the permissionless blockchain systems. And the chain code, the smart contracts in the Hyperledger Fabric are packaged inside a particular construct known as chain code, where it runs in a Docker container, and there is a registry of all the chain codes. So we will get into some of the details of smart contracts and chain code in this session, and the security and crypto services run commonly across. So identity, ledger, contracts. Then we have APIs, events, and SDKs to interact with all these modules in a individual manner or in a group based transactions. So to understand the key features of Hyperledger Fabric, the chain code, as we have mentioned in the previous slide, is the the smart contract. So uh, chain codes are engineered in such a way that they modularized chain. You will understand more about it when you're seeing the architecture diagram. The ledger consists of the interestingly, ledger has a file system module and a database module. That's quite interesting, we should understand. So this ledger consisting of two modules called one module is known as world state or a state database, and then we have specific ledger module. Both of them together gives a very good capability for us to query the database and use the data through these rich queries in various ways for different kind of computations. Channel is a interesting construct here, so that its channel is something like each channel functions as a independent blockchain inside the network. So it's like that's a very, I mean, so these there the we install chain code in the channel, and then we maintain data, private data and the public data inside the channel. So channels provide a high degree of privacy and confidentiality. Now comes the security and membership services. So that's what we have mentioned earlier, the membership service provider. And consensus part, with regard to consensus, Hyperledger Fabric has been evolving from the early versions known as 0.6 to zero point 0.4, zero point 0.6, then a major version known as 1.4, 2.2, 2.3. Now the major consensus algorithm used in the version is called Raft, which is an innovation over a very famous, one of the early consensus algorithm known as Paxos. So let's see the components in Hyperledger Fabric in a diagrammatic manner. As you see in this diagram, the overarching block, the box is the blockchain network. The S indicates the chain code, which are the contracts that are deployed on uh, the peers which are connected in the channel. So P indicates the peers, and O indicates the orderer which is ordering the transactions, applying the consensus. The L block indicates the ledger. So you can see the chain codes are deployed on peers, and the peers which are, they each of them maintain their own ledger copy, and they join a channel, and applications connect to the channel. As we applications are the connecting to the channel, communicate via channel. The security modules, they also communicate via the channel. So as you see here in the diagram, T1 indicates the transaction with the proposal P, and the response to the transaction. When you submit a proposal, you get a response to the proposal, which is endorsed by the endorsing peer. There are different type of peers in Hyperledger Fabric, which we will understand in the coming slides. So this diagram shows major components. So in Hyperledger Fabric, like we heard before, the smart contracts are mentioned as chain code, and the networks use chain code uh, to regulate reading of the content inside the blockchain. Content, we will connect to the content or the data through the state databases. So the data is stored in databases, the state database, and these chain codes interact with the state database. You write your own logic, execution logic also in the chain code, which does the logical processing. And the node supporting endorsement process. The what happens is, after the endorsement, the network install and instantiate the chain code, and then so this happens with the client. Let me show you the flow. First, the transaction proposal comes in from the client. The transactions are simulated by the endorsing peer, as you see in the second step, and then once it is simulated and the something known as a read write set is generated, we get the response. The response is sent back to the client, and then once this much is fine, the transactions are submitted to the orderer. Then the transaction ordering happens and the new block creation happens. Then all these details are delivered through events. If you go a little bit into the details, this is what happens. The applications, the client side decentralized applications, they communicate to the peers through a proposal. They submit the proposal, and the endorsing peers who are friend ending, they execute the chain code to simulate the proposal in the peer. This is interesting. This kind of a simulation, the simulation model is unique to the Hyperledger Fabric architecture. So what happens after this? After the simulation, it creates something known as a read-write set. Once the read-write set is generated properly, the proposal response is sent back, and then once this with the read-write set you get the response, the SDK again submit the transaction to the ordering service. The ordering service then create a batch of transactions based on the configuration we have done. You can group transactions, or either it is based on the minimum number of transactions you mentioned inside the configuration. It could be 10, 20, etc. Or it is based on the block timeout in seconds. And thereafter, once the ordering service create the batch of transactions, then the transactions are committed to the peers, all the peers. So what happens in the committing phase is very important. So the committing peer, they receive batch of transaction from ordering service, they validate transactions, and they validate the endorsement policy. Then they validate the read set version in the state database, commit block into blockchain, and commit valid transactions to the state database. So this much is happening inside a particular transaction. So when you look at this component, what we have is the crucial component is an ordering service, which is connected to peers. Each of the peer has their own ledger where they can contain both block and world state. They also can contain something known as private data for scenarios when you want to maintain some data exclusively within the ledger for private communication. Even when the peers join the channel, they don't want to share all the data in the channel. So such data is maintained in private data. And chain codes are installed and instantiated in the peers through the life cycle. And then the security the identity management is done through a module known as certificate authority and something known as a membership service provider. Each certificate authority has their own certificate database. It could be a cloud-based database. You can use something like Amazon Key Management Service, or you can use a database like PostgreSQL, or by native, an SQLite DB is coming up, is there. Okay, so why this architectural approach is very different? What we have seen in Fabric, how is it very different? Traditional blockchain platforms, both permissioned and permissionless one, follow a sequential execution style. Even if you look at systems like whether permissionless systems like Ethereum, Bitcoin, or Algorand, Polkadot, or you look at the permission systems like Corda or Hashgraph, Hedera Hashgraph, there is a sequential execution style. The transactions are executed after the consent, or they are entwined where all the participants execute the contracts. So it's like transaction ordering and execute architecture. So from the Fabric point of view, Fabric has achieved transactions per second as high as 20,000 or between 3,000 to 20,000, right? So this kind of an order execute architecture limits the scalability, and hence the sequential model has its own challenges. That's why here the model is different. Here Hyperledger Fabric introduces the model where it helps us to prevent the scenario where there will be race conditions or and security issues, or very heavy attacks on the ordering system, right? So this architecture is known as execute order validate architecture, and this execute order validate architecture is a kind of hybrid replication model. As per Hyperledger, it combines passive and active replication in the Byzantine fault-tolerant model. How is it passive? It is passive in the sense that every transaction is executed or endorsed by a subset of peers, not by all the peers. And these peers can do this concurrently, or they can do it in a parallel execution manner without getting into race condition. Okay, so and because of this, transactions of the ledger are written only after consensus is reached. That's why when we saw the diagram, committing transactions, the validation and committing happens only after the consensus is reached, or when the orderer batches all the transactions. So there is initially a passive replication, and then there is an active replication. This hybrid replication supports is made possible by using policies. These policies are known as endorsement policies that helps the Fabric to come up with application specific trust assumptions. For example, you can have specific endorsement policies in different channels. You can have multiple channels in the system. Transactions doesn't have to be constructed all in one order. Okay, so we mentioned about chain codes. Before I get into further details, let me show you Fabric infrastructure quickly. I hope I'm audible till now.
Yeah, you are completely audible.
Okay, and now I'm going into my environment. I hope you can see my environment.
Yes, yes.
Okay, so what I'm going to do is I'm going to show you my Hyperledger Fabric infrastructure. This is the Hyperledger 4.2, which is the long-term supported version. Here I am. Let me start the Fabric infrastructure. So first it will stop any other parallel running infrastructure. All these components are Docker containers. So I think okay, it is now, since this is already a created network, it is now trying to create a channel. I will explain the components once this is done. So it is, so what you are seeing here is it is creating a channel. Initially it is looking at the Docker version, the certificate authority, and then it is creating the network first. Initially it will create the identity, then it is enrolling the certificate authority admin. Okay, you have to look at there is a config file for, this is the certificate module, and this is the config file for the certificate client. So there is a client and server for certificate authority. It is very important that the TLS should be enabled, and the client certificate is stored here. Then there is something known as, basically it comes with a one certificate authority, but if you want more, you can create intermediary certificate authorities. Now after enrolling the certificate authority, you are registering the peer. So this is the way by which you are creating an authenticated identity for the peers, and afterwards the users are created, and then it registers the organization admin. So peers are part of the organizations, and then for the first peer 0, the membership service provider is generated, and then it is generating the TLS certificates, and now it is generating the membership service provider, and then it is generating the membership service provider for the organization admin, and now it is creating the organization 2, and it's enrolling the certificate authority admin. It's registering the peer 0 into the second organization. Now the same steps are repeated for the second organization. Afterwards, what you're seeing is it is creating the peer state database, which is on CouchDB. For this particular this network, it is on CouchDB, the state database. And now you can see all the running containers, the Fabric peers, the CouchDB container, then the orderer, then the certificate authority, and thereafter it is running the command to create the channel. So each channel is a individual blockchain, and then it is taking snapshot. So once the channel is created, you have the details about the channel. Then the peers are joining the channel. Yeah, and then you're fetching the block details, and then you are setting a specific kind of peer known as anger peer, which we will understand shortly. So once this much is done, so it is set anger peer for both for the channel for both the organization, and then it is trying to deploy. It is trying to deploy the chain codes which are already created. Chain code is the contract. First step is installing the chain code on the peer, and then the peer lifecycle begins. The chain code is packaged. Chain code is installed on peer 0 for both the organizations. The chain code query is done. Now after this, the chain code has to be approved on channels. So this is a different approach than what you see in Ethereum, this approval process. This gives furthermore control of the smart contracts. So the chain code definition is approved, and then chain code definition is committed once it is approved, and then uh, afterwards, once the chain code is approved and committed, you can invoke, and you can invoke those chain code to do transactions. So this is the running network. If you, this is something, this is I'm showing something known as fabric samples. You can see lot of sample networks created here. There is a network for auction. There is a network for maintaining private data. There is if you, there is something known as if you create a, if you want to create a highly scalable system that is high throughput, when you want to deploy all this into Kubernetes, this is a sample system with implementation on Kubernetes. If you want to create tokens, these are sample networks for ERC20 and ERC721. So that's about Hyperledger Fabric samples, which you can find it from the Hyperledger organization in GitHub. Now let me come back to the presentation. So we are talking about the chain code here. I think I have some time constraints, so I'm moving a little faster here. So what happens to the chain code? Chain code, what you have seen, you can invoke a chain code, right? Chain code can put the data and get the data. These two functions are used very frequently when you're writing a chain code. So what is the life cycle of a chain code? First, you connect to the peer. If the chain code is already installed, you invoke the chain code for the proposal. Then you get the response from the peer, and then you are requesting to the ordering service to order the transaction. What happens in that stage? Initially, transaction sent to the peers in block. The peers update the ledger using the block. Maybe so only initially the chain code is coming into one peer, but you have a network of 3 peer in an organization. In that case, the transaction is sent to all the other peer by the orderer. Okay, and the chain code generate query and update the response. So I know this is very little time to understand the complete architecture of Hyperledger Fabric, but please understand what you have is peers. Peers join the organizations, and peers join the channel. Organization is a collection of different type of peers, and channel is where multiple organizations come together or peers come together. Okay, so when you look at the data, the architecture, you have a world state where you can have both public data and private data. Private data is useful when you are dealing with privacy protection related use cases. And in the ledger, so the Hyperledger's ledger consists of world state and the blockchain. So the data in the world state can be stored in the form of key value or key value pair. Okay, so this is the general blockchain data structure. I'm just going into the type of peers. Like I mentioned, endorsing peer is the peer which directly interface with the clients or SDK. And then there is anchor peer which does the communication with the other peer. Then there is a third type of peer known as leader peer, and fourth is the common. Every peer is a committer. Okay, so, but we have to understand the difference between anchor peer and leader peer clearly. Anchor peer is a peer in a channel that all the other peers can discover and communicate with. So every organization in a channel will have an anchor peer. Leader peer is something which communicates with the ordering service. When the ordering service must send a block to the peer, it sends to the block to leader peer. Leader peer could be selected either by a voting or it can be selected statically. So here in the latest version of Fabric, we have the Fabric consensus known as the Raft consensus. Raft an improvement over the Paxos consensus, which was proposed by Leslie Lamport in the early 1980s. So it is a very simple consensus model where there is a leader election, and the leader will be elected from followers, and the leader is selected for a term, and once the term is finished, then the leader is selected from the candidates. This diagram shows it very simple. When the starting, everyone is a follower and everyone want to participate in the election, and from all the candidates a leader is selected, and it could be once, or either if uh, there is a majority of vote. Only if the majority of vote is received, the leader will be selected, and then once the term expires, a new leader is elected from the followers. It follows a replicated state machine model. In the Raft consensus, normally we'll have odd number of consenters. It could be 3, 5, 7, 9, etc. So this is how any consensus algorithm can be drawn. Okay, so now we are getting into the crux of our session, Hyperledger Fabric security. So, like we mentioned earlier, the Hyperledger Fabric's threats differ from permissionless chains. Majority of the common attacks like 51% attack or partitioning attack, they are not significant threat to a permission system like Fabric, because here identity is known, identity is validated the moment, even before you join the network, and then the activities are monitored and access is managed by access control list. So here but the attacks, like other attacks like denial of service attacks or consensus manipulation or smart contract vulnerabilities, these attacks become prominent here. And there could be another attacks on the most important component known as membership service provider. Let's look at these attacks. Before that, let us list all these components. The major components are the identity management modules, the certificate authority server and certificate authority client, membership service provider, the policies that we write for endorsement, channel level policies, chain code lifecycle policies. All these policies are important. Then very important to enable TLS, transport layer security. And if you're dealing with very highly confidential use cases, it is good to use a hardware security module in conjunction with all this. Okay, when you look at the functional security of Fabric, connecting TLS encryption and proper certificate handling are two important aspects. So the configuration of certificate authority with proper key management is very important. It could be stored either native or on cloud. And you can also do attribute based access control for the chain code for specific, for example, if you want specific kind of permissions for the clients to validate their permission and their roles before they execute a chain code, that can be done through attribute based access control. And along with, like we mentioned, along with enabling TLS based client authentication on peer node is another very important aspect. Apart from this network level, on the host level also, there could be possible attacks. So that is why on cloud we can use something like AWS key management service, or we can do native encryption on the host. This is the diagrammatic representation of Fabric CA. So this is the network of in an organization. This could be endorsing peer, anchor peer, leader peer. So the first they talk to, this is the endorsing peer, and this could be an anchor peer. Others could be committing peer, or one among them could be leader peer. So the Fabric root server interacts with the intermediate server, and then checks and then through the SDK you check the enrollment, and the Fabric CA client is available, you can connect to the server through command line CLI. You can connect to the CA server using the command line, and you can, if you want high availability for the certificate authority, you can maintain a cluster of certificate authority server. This is how the interaction happens between the root CA and the intermediary CA. Okay, so a certificate authority provides registration features like registration of identities, or if you want to connect with your enterprise LDAP, you can do that. Connect enterprise LDAP and use as the user registry together with the certificate authority. You can issue enrollment certificates which can be validated by the from your client side. You can even revoke the certificates. That's the feature added recently. You can renew the certificate and revoke the certificate. Certificate authority consists of server and the client component. The CS server should always be started with enabling TLS. So when you look at the identity management, we have seen these details. So there are two ways, like we mentioned. The most important way is we generate a digital certificate, an X509 digital certificate issued by certificate authority. In some cases, when you don't want to reveal the identity of the participating nodes or peers, you can use something known as identity mixer, which is a feature recently added. Identity mixer uses the concept of zero knowledge proof. So the identity you can't it's unlinkable. You can't trace the identity of the peers when you're using identity mixer, but it can be verified. So normally the identity verification happens from the membership service provider. Membership service provider is the trusted authority. So it's a component that defines the rules for every organization in Fabric. So in Hyperledger Fabric, channels define a set of organization membership service provider, and then default MSP uses X509 certificate issued by certificate authority. Adopting it's a simple public key infrastructure hierarchical model. That's how you're able to have a root certificate and intermediary certificates. Now, other important component is the policies. The policies represent how members agree on accepting or rejecting changes to the network. For example, you want to say the endorsement should be done by both peer 0 and peer 1. So then you will say and policy. Otherwise, if you want to say if either of the endorsing peers can endorse it, then you use the or policy. So this is how these policies can be written. These policies can be written in the channel, or it can be written also at the chain code level. Now let us quickly look at the attack vectors we mentioned. The denial of service attack is one of the more prominent attack possible on the Hyperledger Fabric system. Other attack vector possible is the consensus manipulation. We have to understand that the consensus algorithms used currently, Raft, is only crash fault tolerant. There is ongoing research going on adding a Byzantine fault tolerant algorithm like BFT Smart. So even regardless of the consensus algorithm used, there could be if there is a dishonest ordering service, a malicious ordering service, that attack vector is quite possible. That's why consensus manipulation is a possible attack vector. Then another possible attack vector is compromise of membership service provider. This membership service provider is able to modify access control to the network. So if any malicious attacker want to perform civil attacks, it can be done by compromising the membership service provider. It could be a rogue insider or through a private key theft, which has to be those chances has to be eliminated to the maximum possible it possible, maximum possible. Like, to mitigate this risk, it is important to follow the best practices with key management and logging every action of the membership service provider, such as certificate creation and revocation. And likewise, for the ordering service node also, it is very important to monitor the ordering service node actions. You can either integrate Splunk or you can use Prometheus with this. So there are a set of attack vectors possible in the chain code, or the risk if you're using any kind of randomness in chain code, or if you're using any external timestamp, or if you are iterating over a map object or calling an external API, using global variables, Go routines, range queries, you have to be very careful because they all open up possibilities of attacks. But if your functionality mandates the use of them, you have to be very careful using them, especially with randomness, timestamp, Go routines, external libraries, global variables, etc. So when you look at these vulnerabilities, the object reification, this is an attack vector possible through a pointer. So using reified objects can cause non-determinism and create race condition. Global variables which are not stored on the ledger can also be uh, another which can also introduce inconsistencies. When you use system timestamp, it is very difficult to ensure that the timestamps are run concurrently in each peer. And like we mentioned, map structure iteration. Due to hidden implementation details of the, if you're writing chain code in Go language, when an iteration over map structure is used, uh, the non-determinism can arise, and then order of key values may change. That could create problems with the data that you're storing in the state database. When you're you doing concurrency with the chain code, if multiple transactions are executed concurrently under high load, the key versions the can change, and it could possibly create key collisions and can even result in double spending. If a transaction has passed from endorsing phase, and it's again, this is also similar, the if the key is manipulated after the endorsement phase, it can before it reaches the validation phase again, there could be a key manipulation attack. So range query is a kind of query that you run on the Fabric's state database. You are running the query across a set of maybe you've run a batch of transactions. Now you want to query them and get compute the value, or you want to compute what has happened in this particular range. All those kind of queries has to be done very carefully. So I think I've crossed the time limit. The other two attack vectors are chain code sandboxing. When the chain code is executed in an isolated chain code Docker container with sufficient privileges, their escape is a possibility. It can be exploited in a malicious way, such as port scanning, or like I mentioned, container escape, identify and exploit vulnerable peers. All those are possibilities. Log injection is another kind of attack vector possible, any corruption of the log messages. So when you look at the mitigations of these attack vectors, importantly, monitoring the orderer, membership service provider, these are very very important. And other important thing is using the once the Byzantine fault tolerant algorithms are available, Hyperledger Fabric would be furthermore secure to BFT, Byzantine BFT kind of attacks. There are like more uh, in the pseudo anonymous endorsing peers, which uses verifiable random functions, are a possibility. And then maybe in the future, when zero knowledge proofs become more easily accessible in Hyperledger Fabric, that could help improve the security of the identity, so that unlinkable identity based verifications can be done. So this diagram shows what are the attacks, possible attacks, and what are the membership service provider. If SGX enabled membership service provider is used, that could be a good solution. That could be like you can use Intel SGX or other hardware security mode, or you can do any other trusted execution environments. That is another possibility to protect the membership service provider. So, smart contract security measures, timeline limitations of chain code execution can be employed. Like if you are using timestamp, timeline limitations could be one possible option. Chain code execution should be performed with privileges other than the root. The Go's crypto randomness package can be used other than any other randomness modules. So limiting the access to the trusted services is the other option. And then very importantly, the key collision should be avoided by doing the version control. The on the when you're using the when you're using there is an option to use composite keys in Hyperledger Fabric. When you do use composite keys with version control, key collision issues can be mitigated. So with this, I would like to conclude the session. Uh, there are more possibilities for privacy protection using private data collections and channels, which due to time limitation, I don't want to go into those details. But with this, what I have covered is what is the general architecture of Hyperledger Fabric, how is it different from other permissioned and permissionless blockchain protocols, and what are the key components for security, and what are the attack vectors, and what are the risk mitigation methods. With this, please let me conclude my session.
Hi, sir. Can you hear us?
Yes, yes.
All right. Yeah, it was kind of a new experience, right, for most of us into the world of Hyperledger security, because we often talk about the security space of blockchain, the smart contracts, Ethereum, Binance, and yeah, the normal EVM based chains, and yeah. So like right now, we just started talking about the Rust based security,
Wow.
considering Polkadots, Solana, and all. But yes, talking about this space of Hyperledger is I guess pretty new and pretty much unexplored right now. And yes, you have actually given insights, and yes, people are saying this was actually interesting. But I'm sure people are having less information about this Hyperledger security. Like let's keep this in the same category where the Ethereum was back in 2017-18. The
Yeah,
Ethereum security pretty much unexplored, scattered information. Everyone was
yeah,
trying to learn, but it was pretty hard for everyone to get into it. And I guess the same thing is going on with Hyperledger security. The
yeah,
chain code and things are new, but yes, we'll surely be having a boost after this session, and
yeah,
much more with these kind of sessions. So we want these kind of sessions at a scale of 10x to promote Hyperledger security as well.
yeah,
But yes, oh my god, wow, how many things were there, so many new things that I have learned, and I will be exploring myself Hyperledger security.
That would be
And
great,
yes,
Tejaswa and Arun. See, this is a differently engineered system.
right,
So their design philosophy itself is very different. So it took me also a while to understand this. But if you understand it, it would be very interesting to look at from a distributed system standpoint. You will get to play around with lot of security components which are used
right,
in industry and enterprises traditionally, and to
yes,
test how secure they are. So it's an interesting journey if people like you who are deep into the security world comes into Hyperledger Fabric security. I am very sure we'll have more utilities, more libraries, more security audit reports would be there,
mhm,
and that would really
right,
help this enterprises. Not only enterprises, there are a lot
mhm,
of startups which are
right,
doing a great work on Hyperledger Fabric. So they will all benefit a lot, and the community will benefit a lot if security researchers spend more time with Fabric. That's why I wanted to give this introduction.
right,
Please
yes.
consider this only as
And
an
it was,
introduction session.
yes, it was kind of something we can take beyond blockchain, right? So,
Yeah,
it's like the conference right now we can point it out, not just blockchain specific, we can say decentralized security, right? So
yeah, yeah.
it's not just limited to blockchain now. So I guess hopefully sooner we will be having more talks over like DAX and lattices as well, like beyond even Hyperledger and things like that.
Yeah,
So
yeah.
hoping the best. But yes, so this was completely new insights from your side. And what we can say, we can just say
I was
thanks you.
actually thinking, should I take a session on Polkadot security or Fabric security? So I've
You're always
chosen
free to do
Fabric
so, sir.
because I wanted more I wanted more attention on this,
Mhm,
if possible, and more work, because there are only very few libraries which are doing chain code audits,
mhm,
maybe in the public domain. But then
mhm,
if a community looks at it, it will be great.
mhm.
It will be good for the general community and also for the Hyperledger ecosystem.
Right, right. Yes, that will definitely help a lot. And like, if you want us to share some resources, video slides, please let us know. Any approach that you want to provide to the new learners, right? How to get started? Like, if they want to learn, for first of all the Hyperledger itself, the tech stack, and then come into the security part itself. So if you have a general approach to follow, please let us know. We'll
Yeah,
link
yeah.
and attach
Can
to
I
your
share
slide.
one more slide? I mean,
Yeah, yeah,
I've
please,
created
please, sure.
I'm just trying to, yeah,
Mhm.
I'll just show you in GitHub. Please, I've curated, uh, if you come to, I've curated set of material Fabric which could
Mhm.
be useful. I will share it, this my curation. So you will get material on different aspects of Hyperledger Fabric: consensus,
Mhm.
performance, chain code, best practices, testing,
Mhm.
security. So please let me share this link in the chat.
Mhm.
I am not sure if I'm able to share in the chat. I'll share this with
Uh,
you all.
okay. Arnab, have you received it?
Uh,
No, no, I'm not able to share the chat.
okay.
Okay.
You can just drop in the private chat and we will just
You
share.
can drop in the private chat that we have, and you can
Yeah, yeah.
share.
I just shared in my
Yes,
private chat to
got it,
Tejaswa.
got it.
So thank you once again, team RazzorSec, Arunim, Tejaswa,
Thank you.
Quill Audits for giving me opportunity. This were in the second edition of Unchained. It's a great honor.
It's an honor for us
Thank you,
to
thank
have
you.
you with us. But yep.
I really enjoy this community and fraternity.
Mhm.
Wish you all the very best for this ecosystem and
Thank you.
this platform.
Thank you.
And yes, yeah, thank you so much for all the best wishes.
Thank you.
And we always will be seeking your support. Like
Pleasure.
as individual members and as community members as well. So once again, thanks for your contributions and just keep doing it. We don't want you to stop like any moment. Just keep on doing it and
Sure,
just
sure. With all your support, I will
yes.
contribute more as much as I can. Thank you once again.
Hmm.
Signing off.
Right. Thank you so much, sir. Have a great day. Bye
You
bye.
too. Bye bye.
All right.
Yeah.
That
All
was
right.
quite wonderful. Like Hyperledger security and all. Okay, that's great.
That was quite a power-packed session.
Yeah, it was a
that we
powerful
had.
session, and I knew this time would be less for him. Uh,
Yeah.
so yes, but yes, we will be sharing the slides with all the viewers so that you can just quickly go through them, and if you have any question, we can just forward them with the speakers and give you the answers.
Yeah.
So coming up with us is
We have
Daniel.
Daniel. Yeah.
Right. So please. Hi, Daniel.
Hello.
How are you? All good.
Good. Good.
Yeah.
Can you hear me
What,
well?
what a nice setup that you have. Like, I guess you're like coming straight from a studio itself.
Yes. Well, a studio in my garage, but yes, I actually before doing blockchain security, I did lighting
Mhm,
programming and actually did
mhm,
theatrical lighting as a kid.
mhm.
And
Okay, so we
so
have a garage hacker as well. Okay.
yes, but I don't
Great.
have any like professional lights, so I just
Yeah.
got
No,
little
that
lights
is
from the
actually
store and stuck them
looking
behind me.
sick. Yeah, that is actually looking pretty sick. The completely natural background with all the light up and all. Yes, but that was wonderful. So we won't be taking much time, and like a quick introduction from our side. Daniel is the security engineer, senior security engineer at Origin Protocol. He do the security researchers. Like we often see him like on a regular basis on Twitter. We follow him, and he constantly posts about the smart contract attacks, like some protocol like getting exploited in a daylight and things like going on, like all the crazy talks. Yes, so with that, I will leave the stage to him, and the stage is all yours, Daniel.
Great. I will start sharing my screen here.
Perfect.
And can you tell me if I'm sharing?
Yes, you.
Okay.
Yes, it's fine. Perfectly visible.
Wonderful. Okay, so today I'm going to talk about understanding hacks. And the first question is why? So if you're here listening, there's probably three reasons. One, you're trying to do bounty hunting, security research, find bugs in other contracts and save them from getting hacked. Two, you might be trying to write contracts and not get hacked, which might even be harder. Or three, you might be trying to hack contracts. And if you're trying to do that, then you're not my friend and I buy you no drinks. But for the first two, securing contracts and helping save other contracts, bounty hunting, the most important thing you can do is understand how contracts get hacked. That's the foundation and the basis for everything you do after that. So there's a lot of things that are easy to find in audits and get found in audits. And that's kind of one class of things, or the audit kind of things. And then there's a second class, which is the things that actually sync contracts. And by following smart contract hacks, you can learn a focused view in exactly the proportions that they happen in the wild of what actually gets contracts wrecked. How does money get stolen? I think it's the best way to learn, other than like a first few minutes of, or, read about the vulnerabilities, know how to write Solidity. But for ongoing education and for turning yourself from a beginner to an expert, nothing really beats reading hacks. And there's kind of two ways to go about it. One way is to read what other people say about it. And the other way is to actually go into the guts yourself, dive in there and find out what really happened. Look at the code yourself. There is no substitute at all for actually looking at the code. Sometimes people make generalizations when they're talking about a contract hack online. Sometimes what is said is not actually true about what the hack was. Sometimes there's more to it than is talked about. So, and possibly the biggest one is you get used to seeing these vulnerabilities inside actual contracts, which when you're trying to secure your own contract, you write some code and then you think, wow, this looks like that hack that happened 6 months ago. And then you look at your code a lot harder then. Or if you're scrolling through something else, you know, it triggers a pattern memory when you've seen this kind of pattern happening before. So looking at smart contract hacks is, I think, the best thing you can do to really go from beginner to an expert on smart contract security. One of the reasons why defending against attackers is so hard in this area and why so much money gets stolen is because attackers have superpowers that bank robbers could only hardly dream of. So if you have this heist movie, they like have to go get the plans to the place they're going to attack, and then they have to go find in a warehouse and they have to build a replica of the vault. And then maybe they practice some, and then they go to the actual place and it doesn't work out like they planned. But in smart contract attacking, it's not like that. An attacker can not only get the exact plans of your contract just by looking on Etherscan, they can have a complete practice environment by typing a single command, fork copy of mainnet where they can work on your stuff without you seeing it. They can see every single transaction that's gone through your system and what everything in your system did. When they're practicing attacking you, they get to see kind of every defense and try and attack every defense in their system. And then once they've perfected it down to a run that will work, they can just execute it. And all that happens in a single transaction and boom, money's gone. This allows even for crazier attacks like the second cream, or one of the last cream attack, where the attacker actually borrowed and gave away $16 million, but literally gave away $16 million as part of their attack. And yet they were able to be so confident that this attack is going to work successfully that they're able to do something like that. So defending smart contracts is one of the hardest jobs in the world, hardest programming task in the world. But if you're learning from attackers, you have superpowers because you get to essentially walk through every single step that the attacker made down to every single bytecode instruction that got executed if you feel like it. You get to look at the perfect map of the victim contract, the perfect map of the attacker contract, and see every step that happened. So there's nothing like it for learning from an exploit. You don't have to just read about it. You don't just have to look at an exploit and kind of guess what happens. You can perfectly step through an attack. It's amazing. All right. So who am I? I am a senior engineer at Origin Protocol. We have a DeFi product with about $200 million in it. We also do NFT sales. We're also hiring. We've been around since the ICO craze and are still building. I personally grew up starting out on websites, just building websites, and then moved on to embedded software, some industrial programming, lights, like $1,000 lights, a lot of power supply coding, and then into blockchain, smart contracts, and eventually into blockchain security. For the past year, I've followed and dug into every single DeFi hack that has happened that has a reasonable amount stolen. My personal threshold is $1 million, although usually if I hear about it, I'll check it out otherwise. That's really me. Let's go into an attack. So when you're looking at an attack, there's 4 things you can look at, and you can focus on them or look at them in any way you want to. You've got the execution flow of what code executed, what contract called what contract with what parameters. You have the attack contract, which is almost always in bytecode and isn't easy to read. And then you have the victim contract, which would be easy to read, except for the fact that it's usually a half dozen contracts or more. And then you have the flow of funds. And you can start at any one of these points So where do you start? Well, for one thing, I'm making this diagram look much simpler than it really is, because this is the reality. Is you've also got flash loans going on, you've got AMMs, you've got some kind of random contract that the attacker is talking to, you may have WETH, Oracle manipulation, maybe there's some proxy contracts involved, more than one victim contract. The victim contract may be sending off to other strategies, but really you can pretty much boil it down to you're trying to look at these things and just focus on that. So when there's an attack, there's almost always the same pattern that goes into an attack. First, the attacker prepares some funds. They may get a flash loan from somewhere. In some contracts, you can kind of skip this step because they're able just to get money. But most DeFi attacks start with the attacker getting some funds into position somehow. Then the attacker puts the victim contract into a bad state, or it twists the world around in some way that the victim contract is going to get messed up. This can be as simple as a single transaction. This can be as complicated as manipulating a whole lot of different things. And then the attacker tries to get money from that bad state that they put the contract into. And then lastly, the attacker may need to repay flash loans and then transfer the stolen funds out. Sometimes they'll sell them as well. So all that goes into it. But what you really want to focus on, jumping back here to this diagram, is you want to focus on the bug, finding what the bug is in the victim contract that allowed all this to happen. So rather than continuing to talk about this from a theoretical point of view, let's walk through an attack that happened yesterday, about 24 hours ago. And so we'll step through actually how we would solve on this attack here. So I'm pulling up Etherscan. We can see that somebody swapped some Rimco tokens on Etherscan. We can see that there was about 1.2 Etherscan transferred here. This is kind of tokens transferred. And if you look kind of carefully at this, the only real takeaway you might have from this page is that somebody swapped a very big number of Rimco tokens. So how do we go from this, just looking on Etherscan, into finding out what the hack was, what the vulnerability was? My favorite tool is ETHTX. So I'm going to go ethtx.info and paste in this transaction. And it'll take it a second to trace it through. Up here is events that were emitted in the transaction. We can just see that there's some token transfers here. This is one of my second favorite features here, is that this shows you at the end of this transaction what balance has changed. And so looking at this, I can see that the attacker spent 0.6 ETH, and at the end of the day, this address gained 1.2 ETH. And I can see that these two Uniswap pairs lost a small amount of ETH each. And so it looks like the attack ended up by stealing from the Uniswap pairs, and the attacker ended up with a small profit. So here is the execution trace. This is what I love about ETHTX the most, is that you can see all the calls that one contract made to another contract, and you can see what it is, or you can see what values they return and what was passed to them. So here we can see this is the attacker address sent to this proxy. Now I happen to know that this attack was actually front run. So this is kind of a generic proxy that allowed this MEV bot to execute all the commands that the attacker was actually trying to attack or trying to run. So the first thing it does is does a balance of WETH to find out how much WETH is here. This is almost certainly just for the attacker or the front runners to find out if they've lost money or gained money on this transaction. And so here comes a call into an actual contract. This may be into the attack contract itself. I'm not sure. We can see that the Rimco token had a burn called on it. We can see that Rimco token was transferred to Uniswap. We see a swap right here that looks normal, transfers out a bunch of ETH, or tiny bit of ETH. And then we can see another transfer to Uniswap, another swap, and then basically collecting the money. So if we're going to focus down on this, we can ignore all this, and we can ignore all this. And once we look a little bit closer, we realize, this attacker is stealing, or is basically transferring a crazy amount of money to Uniswap that they didn't start out with. So if this is more the step 3, the collect the funds part of the attack. And so that pretty much leaves us with this burn function here. Somehow this burn function got the attacker a whole lot of money. So now let's go in and take a look at the victim contract here. From here, I can just click on the token, go right to the contract, and look at the code. Now we saw that the burn function was suspicious. And so now we look at this thing, and now we put on our regular hat of how did burning one token result in the attacker having tons of tokens. And so we step in here into this first method. We know that count was called with a 1. We see it subtracting a 1. And Solidity, up until the most recent versions, would underflow if you did a subtraction. So what's happening here is the balance of the sender is set to 0. When a 1 is subtracted, it basically turns into infinity. And that infinity then is used to, well, at that point, the attacker has all the tokens and can just transfer it to wherever they want. So this line right here is the bug. That's why this one was an easy one to understand. When it came in, it took like 60 seconds to go through those steps to see this bug. Not everything is that easy. Some can be like an hour or more, or 2 hours, or a whole team of people figuring out what happened. But that's one easy one. So let's go right here. One thing that is really helpful to do as you're working through this is to have a text file and stick notes into it. Copy and paste your notes in, just in there. Take every transaction hash you're looking into, write contract addresses down that are getting called, and if the attacker's contract address. I tend to start with a very quick look at the money to see who gained, who lost. And then the main thing for me is looking at the execution flow. Cut out the stuff that's not useful to you. Attacks often spend a lot of their transactions, maybe even the majority of their transactions, on things that are not actually the vulnerability. Find where things go weird. Usually that's where the vulnerability is opened, and then find the bug in the victim contract. So that's kind of the standard way of working through a bug. So now I've labeled this one medium. It is actually not medium. Well, it's way harder than the other one, less hard than mini. So we'll go take a look at this transaction here for a second. I keep doing this. I'll stop eventually. We'll go over to ETH again. Now this one we can see that there were a lot more events going on. If we look at the balances, we can see that this transaction ended up netting the sender about 45 ETH. And ended up netting the attacking contract about 145 ETH, minus the 42 ETH that it spent. But anyway, this was actually a part of a whole bunch of these transactions were looped and sent over and over again. So the attacker actually made off with maybe $30 million out of all of these. But in looking at this to see who the winner is, the attacker is clearly a winner. Who the loser is, this CR ETH contract, is a loser, as well as whatever this contract is quite a loser. So let's go down and look into the execution trace. And again, instead of being simple like the last one, this one's kind of complicated. Again, we're going to work on narrowing our way down. We see that there's a flash loan that comes in right here with this swap. And then this receiver right here, this is where it's coming into the flash loan. So we can kind of skip everything above that as being kind of irrelevant to finding out where things go weird. The attacker approves WETH, withdraws some WETH into ETH, mints some compound ETH here, and we can see that step through. So they basically lend 500 ETH to compound. Then they borrow AMP from compound. And then let's see what happens now. They create some kind of new contract. They move the money around to the new contract. They move the AMP that they borrowed around. Then from the new contract, they borrow more AMP. Oh, they transferred the, oh no, they liquidate it. And then they redeem ETH. And somehow in this process, they came out with 542 instead of what they put in, instead of 500. So somewhere in this, they made a profit. So somewhere in all this is something weird is happening. Now, this took me a while to figure out last time, or actually other people figured it out first. But if we look here, when this transfer happens, it's actually calling the attacker contract. Right here is a call back to the attacker contract during this AMP transfer. And so if we open this up to see what happens, we see that there's actually a borrow happening inside this borrow. There's a double borrow going on. So this appears to be a reentrancy bug. If I actually click on this right now, I'll be seeing the correctly patched version of this function. So it's not going to be super useful. So I have to say what happened after looking at this. So this attack was a reentrancy bug attack on a borrow. The problem was that the compound contracts, which these cream contracts were based off of, the way the borrow function was written was vulnerable to a reentrancy bug, and was classically vulnerable to reentrancy bug. However, the overall contract was protected by a reentrancy guard that would prevent you from calling the same contract twice from inside itself. The way the attackers worked around this is they actually, the reentrancy guard was per compound contract or cream contract, and here they're on the AMP contract and they start a borrow, and then in reentering they start a borrow onto the ETH contract. And so both contracts reentrancy guards are working, and yet they were still able to reenter the system as a whole. So that was kind of the takeaway from learning from that. I'm just going to leave it there on this attack, but that's kind of how I worked through finding it or reading up on it afterwards. So bugs in smart contracts usually have one of three causes. The first is the contract writer did something stupid. Sometimes this is as simple as leaving off an authentication check, and so that anybody can set themselves as the governor, or writing your authentication check badly. Kind of the second one is a typical common vulnerability. Now this last one was a really advanced use of a typical common reentrancy vulnerability, but the patterns are kind of there. It's kind of easy to spot. The most common reason you get is for big hacks is that the universe is way more complicated than everyone thought. And this hack is also about half this way because the contracts had reentrancy protection, and yet by calling multiple contracts, the reentrancy protection could be bypassed, could be completely working successfully, but fail to protect. So a lot of hacks end up being complicated. And just because the attack is complicated, oftentimes reading up on it takes a lot of deductive and just figuring. A hard attack. Now, I'm not actually going to walk through one of these, but in the last month or two, some contracts had been saved before the attacker even had time to run their code. The attacker deployed their contract to run the attack. People were able to decode the attack, figure out what the plan was without any transactions running, but by just looking at the attacker contract, and then save the funds before the attack could actually execute. That's much harder because you don't have this execution trace anymore. And I'm not actually going to go walk through figuring that out right now. If you want to simulate it, you can take any attack that actually happened and make yourself not look at the transaction traces, not look at the flow of money, and disassemble and work your way through the attack contract to find out what it was doing to get into the victim contract. All right, that is pretty much the end, but I was going to let people ask questions and yeah, see if anybody has questions here.
Oh yes, yeah. So we have a couple of questions, and wow, like, yeah, we have seen like your approach, basically, like how you actually rip apart a bug, we can say, right? So that was very insightful, and going over all those ETX transactions and decoding all the stuff, right? So yep, so that was pretty much it. And yes, we have a couple of questions. One from Muhammad. He's asking like, you said that that contract is written in bytecode. So how do you write a whole contract in bytecode?
The attack contract, well, the reason why you're working from bytecode is because the attacker does not actually verify the contract on Etherscan. And so that's why you're working from the bytecode. It's not actually written in bytecode. It's the attack contracts are almost always still written in Solidity. But the only thing you have access to is the bytecode. You can get a sort of decompile of it on Etherscan, but if you search for Solidity decompilers, there's a couple websites you can paste in the contract address, and it will give you something that's a little bit more readable. That's kind of the answer to that question. On the Rimco token attack, there's not a public postmortem. I think the project appears to be pretty dead. I've contacted them. And yesterday morning and haven't heard anything back from them. So the post-mortem is pretty much my Twitter post at Daniel VF on Twitter.
Yeah, I actually have seen that. That
Yes.
You in the 112, I remembered from the post. All right. So yeah, it was pretty amazing, and yes, going from easy, medium, and hard ones, right? So yeah, we'll still be waiting for like decoding some hard bugs, like in maybe in future events. But yes, that was great. So yes, people are kind of appreciating the talk, and thanks for joining.
Thank you.
And yes,
Awesome. Well, I just kind of end by saying, these things that look extremely hard in the end almost always boil down to something extremely simple. And so that's what I always try to do, is find out after, the giant pages of things that happened, what's the simple thing that went wrong, because that's the learning I carry into writing smart contracts, and that's the learning I carry away into looking for future bugs. Even though big attacks often are very complicated, they're almost always there's a couple small, one or a couple small vulnerabilities. So your takeaway coming away from analyzing a contract is what was the little vulnerability inside all of that. To answer the question about, any answers to reentrancy guards being bypassed, there's kind of three different approaches there. One is be very careful which contracts you trust and only work from a whitelist. That's why Compound did not get hacked, is because they did not have any tokens that could call another token in the middle of a transfer, whereas Cream approved a token that could be whitelisted a token that could be used for a reentrancy attack. Secondly, in a case like this where you've got multiple contracts working, you can have a single master contract that prevents any kind of reentrancy attack from, or provides you a single global lock across all the contracts. So instead of you setting a value on your own contract when you start work, you set a value, you call this global lock and say, hey, lock everything, and now I'm done once you're done. Also, you can write your functions, individual functions, so they're not reentrancy vulnerable, which is what Compound and Cream ended up doing, is just moving that transfer down to the very end of the borrow function instead of in the middle. And that's was enough to solve it there.
Right, great. And I actually wanted to know, like, what are the top three bugs that you would recommend a guy like who's pretty new into the DeFi security space and wanted to learn some attack vectors. So, what are the three most, you can say, widely exploited bugs that you would recommend someone to learn, or like we see on a regular basis?
Mm-hmm. I'd say the three most common vulnerabilities in DeFi world are Oracle manipulation, where you think you're getting a price for something, and while your transaction's running or around your transaction, somebody runs in there and changes the price so that you think that something's cheap's expensive or something's expensive is cheap, and then runs the wrong thing. That's not so much a direct smart contract vulnerability, although it is, but it's not something that's written right there in the code. So that's probably the most common DeFi vulnerability. Reentrancy bugs are the classic Solidity vulnerability. That was the very first big hack, was a reentrancy bug. It's something that really can just trip you up because it's not something you expect. It's not something that's visible from the code. And then lastly would just be making a stupid mistake. It's so easy to just forget a line, you don't unit test, or you do unit test the success path, and of course it works for the success, but it fails otherwise. So, if you have a function that should require authentication, write a unit test that tries to call that function as an unauthenticated user and see if it fails and blows up. Because then if it dies, then it's just good. You have to be able to test the failure path as well, I guess. Any tips for understanding math-heavy contracts? I don't really, if you're talking about math-heavy contracts, the first thing that would come to my mind would be Curve, which if you look at the like Curve 3-pool source code or something, it goes deep math fast. For that, the simplest way for me to understand something like that and to see the behaviors is to use some kind of fork thing and send different transaction amounts to it. Like take in your fork, take $400 million or $1 billion from one of Binance's accounts, transfer it through Curve, and see what happens out the other end. Maybe do that at several different amounts and make a little chart of what actually happens when that happens. Because speaking of Curve 3-pool, it's not intuitive how it actually behaves. But as far as understanding the math, I don't have any real solutions to actually understanding the math. Older versions of Solidity had a bug where you could do underflows like we just saw in that easy one. Fortunately, anything Solidity 8 and above now by default is safe when it's doing math instead of might wrap around.
Right,
but,
right. Mm-hmm. Yeah, please go ahead. Sorry for interrupting.
Oh, okay. For Solidity versions less than 8, anytime you see a plus sign, a minus sign, a multiply sign, or a divide sign, you can be really concerned because those are unsafe in previous versions of Solidity.
Right. That is absolutely true. And yeah, so I would also recommend just going deep down into the maths of, let's say, Uniswap, right? The curve we have, the different curve, like the curve that they follows, that's multiplied by y equal to k, all the product mathematical formulas that we have on the basis of which you get actual reserve price, and also just deep down into that. And yes, somebody has asked, like, a strong knowledge of maths is required for blockchain security.
I don't think it's required at all. It's very rarely a math problem. And the things that are even half math end up being fairly common vulnerabilities. Really all you had to know is if I trade a whole bunch of this coin, it makes the price move up or it makes the price move down. And then you figure out what effect that has on the contract. Almost all the bugs are not, or I don't think I've seen a single contract attack that really required a deep understanding. I'll take that back. I've only seen one smart contract attack that required a more than surface level understanding of prices, just that prices change when you sell. Everything else, so much of DeFi hacks are things that have been seen before. So as you go through this over if you go through every hack that happens over a 3-month period, you've probably seen 95% of the vulnerabilities that take place. It's very rare that an attack actually comes in with a completely new vulnerability.
Correct, that's correct. And one more thing that I actually wanted to ask, we discussed that at the very start of our event, right? The notion of security, right? The notion of security, which was there, if we talk about back in 2018, right? And the notion of security right now, we are seeing like a lot of hacks, like literally occurring every other day. We are seeing lots of bounties as well coming out, and people are like, protocols are actually interested, even they are live already running and serving users, still they wanted to make sure that there should not be any undiscovered bugs. So according to you, how do you take it, and according to you, what is the notion of security right now?
I think that smart contracts are more secure than they have ever been. However, given that there's more of them, there's still, I think, more bugs than there have been. One thing that we see in blockchain security is that an attacker will figure out kind of a new angle onto attacking contracts. And then that kind of contract all over the ecosystem will get hit from many different attackers for similar styles of bugs. And so for a while, there were classic attacks on big name DeFi protocols. We're just coming out of, or maybe we're still in, a period of attack on bridge contracts. This is one of the really big reasons for, if you follow the hacks as they happen, if you're trying to secure contracts, then that gives you the leg up on, what's in style. And when a new vulnerability comes along, you can make sure that your contracts are secure. So that's why I do that. Secondly, if you're working from a bounty point of view, if a whole new style of attack starts happening, then you're also up with, what's currently coming into style. Give me just a second, think on the rest of your question. I think the bounties are really economically right. So much money is being stolen right now that even paying even bigger bounties than we're currently seeing still makes sense, is still quite the profit for the protocols. Over time, eventually, hopefully, there'll be enough. Maybe we'll see fewer attacks and more white hats, which would be even if bounties are paying out $50 million in bounties a year or $100 million in bounties a year, that'd be a tremendous profit over what we're currently seeing on the attack side.
Right. So I think we can say it's directly proportional to the total value logged, right, in the DeFi ecosystem. Yes. The more funds we will be having, and the more number of amounts of white hats, and the number of attackers we'll be having in the space as well. So Jean has asking like how to apply for blockchain security engineer position. Mhm.
Well, if you found a critical bug in a contract and got your name up on it, that probably would throw you right to the critical, or to the the front of the line. One of the great things about bounty hunting side is that nobody has to give you permission to do this. Granted, nobody pays you until you find something, but if you're interested in getting started in it, that's a wonderful thing. It's completely permissionless, trustless. use Immunify or something, so that they work on your behalf to get you paid afterwards. But that's how I would start if I were new to the field. Otherwise, if you are already trained in security, or already know auditing or security stuff, then you might want to work at an auditor place. There is way less good guys in this ecosystem right now than there needs to be, and so the pay is high and people are desperate for people. So it's a great time to get in.
Right, absolutely true. And just hoping for a more number of whiteheads joining us and leading us, at least the whitehead side, because we are seeing like new attacks on a daily basis, and it makes our job a little bit difficult because we have to explore what has actually happened in that attack and what was the vector. Because as a security auditor, we have to replicate that the same strategy onto our next audit and to find out whether it is there or not. Yes. So, like, if we have more and more people with us, we'll be securing more projects. So, with that, I would just want to say thank you, Daniel, for being a part of UnChained and for sharing your valuable insights, your approach. Basically, I actually have got a DM from our own internal team, and he wanted to actually know what is your approach, basically how you uh, go ahead and approach a attack that has happened, approach a bug that has occurred. So yep, you've already shared that with us. So yep, with that, thank you so much, and it was a wonderful session. And hoping to see you soon, probably in another event. And keep rocking. Yeah, congrats,
Thank you
hacker.
so much. It was great to
Yes.
be here, and thank you.
Right.
You have a great one.
Yeah. Have a great day. Bye bye, Daniel.
Bye.
See you soon. What's up, bro, name?
Yeah, I mean, how you doing, man?
Ah, where's my spectacles? Yeah, I want only. Yes. You don't want to see my dark circles,
Yeah,
don't you? Yeah.
everyone has got them these days.
Yes. But yes, we are trying our best to
Yeah.
secure things up. And who we have with us? I guess Henry, right?
Yeah.
All right. Another great concept or aspect. Hi, Henry. How are
Hi
you?
everyone. Hey, I'm
Yeah,
doing
it's so
good.
nice to
Yeah,
see you with us.
nice to see you guys too.
All right, so right now we have Andre, and he's the formal verification engineer straight from runtime verification, and
Yeah,
it's still, we can say, a less explored area, right, in terms of security, because we go ahead with audits and we still often miss out formal verification, which is still a critical component and can like provide us some many like undiscovered bugs that probably would not be possible with some manual testing and all. So with that, Andre, thank you so much for joining us. And with that, the stage is all yours. I know you have a lot of things to share, and we all are excited for you.
all right, thank you. So I'm just gonna share my screen right now.
Right.
Just let me know if you guys can see the screen.
Yes, it's visible, completely
Yeah,
fine.
great. So, hi everyone, I'm Andrei Vacaru. I'm a K developer mostly at Runtime Verification Incorporated. And today I will talk about formally verifying smart contracts. And I'll be using KVM, which is a K implementation of the Ethereum virtual machine. It's fully faithful with other implementations, and it's also a K formal semantics. Meaning that we can use it to do formal verification on Ethereum programs. So, as an overview, I'm gonna go and explain what K framework is, what formal verification and symbolic execution is, and then I'm gonna show you what is our approach to formal verification and have a short demo session. So real quick, Runtime Verification Incorporated is formal methods company. We have serviced before clients in automotive and aeronautics companies. Now we're mostly focused on blockchain clients, and the general mission is to improve basically the state of security and the quality and the correctness of the code across the board. So, all right, what's K? So K is a mathematical modeling language. So basically you build mathematical models in K. One of the key features is that those modules are actually executable. So for example, you can take a test suite and execute it against the K Ethereum virtual machine, the K EVM, which is actually the mathematical model of the Ethereum virtual machine in K. And this also allows you to make proofs on it. So K has two backends which are currently in use. The LLVM backend, which is mostly for concrete execution, so it gives you a fast interpreter, and the Haskell backend, which is for symbolic execution. Okay. So, for example, if you were to say to wanting to make a new programming language, you could choose to write it either in C or in K, let's say. So if you choose to write it in C, then what you would get is a very fast execution, a very fast interpreter. But if you choose to write it in K instead, you still get execution, which is not as fast as if it was written in C, but you would also get symbolic execution, which gives you the ability to write proofs. So that's the reason you would choose to implement it in K. Also, the advantages are that you would develop a semantics for a programming language or that mathematical module, and you would save the implementation effort for multiple tools which K provides you. Also, for example, if you have multiple models in implemented, then upgrading one tool, like for example upgrading the compiler, would benefit all the other models which you have implemented in K. Okay. Now, formal verification, it's a pretty broad term which means different things for different people. Basically, formal verification is the process of checking that design satisfies its system requirements. In other words, to check if the code behaves as expected using some formalism. So testing is a very good way to show the presence of bugs, but it can't show the absence of bugs. So as a scenario, you would write some tests, you would find some bugs, you would fix that bugs, but you have no guarantee that there are no other bugs in your contract. So to prove that there are no bugs, you have to do this mathematically, like a mathematical proof, which you do on a pen and paper, but this time we have computers, which help us very much because the proofs can get pretty big. So what do you need? You need the mathematical model of the programming language. As I said, we have the KEVM. The next step would be to have a specification of your program written in the same language. So basically, a specification is initially written in a very informal way, like an auditor has a chat with or sits at the table and discuss with the code developers, and they agree on what's the behavior of the code and what it shall do. So as I said, it's a manual process and it's informal. So the next step, it would be to take that specification and translate it into K. And since both the specification and the semantics of the virtual machine are both written in K, they would work very good together. And we would actually use the prover to see if the proof, if the specification passes. So it's key to know what this gives you and what it doesn't give you. So people think like if the program is formally verified, then it's 100% safe, and this is not the case. When you're doing formal verification, you're verifying that a specific or a very exact specification of your contract is true. The same like you're doing testing. For example, you have a test which passes. That's very good. It means that scenario is working, but you have no guarantee about other scenarios. So like in testing, you have to think about all the corner cases and all the things you want to prove. Okay. So yeah, as an example, if you would have a proof on a transfer form function for an ERC20 contract, then this wouldn't give you any guarantee for an approved function or any other function of the token. Okay, so yeah, I'd like to talk a bit about symbolic execution, and I'm gonna go a bit back and forth with testing. So as I said, with testing, you're picking specific scenarios and you're just doing sanity checks for it. So let's say we have a contract, and this contract is in an initial state as 0, and it would have a function like deposit to deposit some tokens or I don't know, some value. And this function would have only a single argument. And in a test, you would write a test using a concrete value like 3. And this would have a very clear and specific execution path from start to finish. But in reality, most of the functions have also branching points, like if statements, require clauses, assertion clauses, and so on. So each branching point makes a different execution path. So you would have to take all the cases in consideration. So what symbolic execution does is it takes a symbolic value, an X in this case, like an identifier, and instead of going and iterating through all the values of the argument type, so for example, if in EVM we would have an EVM word, which would be a value somewhere between 0 and 2 to the power of 256. So instead of iterating through all of that values, we would have a single X value, symbolic one, and we would go through the execution process, and we would do some kind of analytical reasoning. So what you get is this entire space of execution path that encompass all the cases that X could take. And as I said, instead of looking at each execution path, we would do it in a closed form and analytical way. So in the end, we would get a single state description, but that state contains the symbolic value, and it would represent a bunch of states. Yeah, so, and again, holding a symbolic value would give, would be a lot less resource intensive, because you wouldn't have to go, as I said, through all the possible values which an argument might take. Yeah, so again, testing can prove the presence of a bug, but because you have the specific execution trace that shows you the presence of the bug, it can't prove the absence of bugs because you're not checking any values there. So we're doing formal verification to get the entire diagram here. But you have to remember that formal verification, it's not a magic bullet. It's not like you're doing it once and your contract's secure. It will give you a high confidence only for the properties and symbolic tests which you have written. Okay. So as I said before, we are using the KEVM, which is the K implementation of the Ethereum virtual machine. Here we have the repository. It would take some while to set up, so if you want to follow along, I suggest that you wait for this presentation to finish, and then you will have all the slides and this video, and you could follow along and do it yourself. So, as I said, is the full implementation of EVM. We tested it against the same test suite that other clients like Geth tested. Similar for Ethereum CPP and Ethereum JSVM, we use the same test suite for all the Ethereum tests. So we know that we have a faithful implementation of the EVM in our mathematical modeling language. So yeah, we also have release instructions. We have instructions if you want to build it from source. Basically, you would have to clone the repository, fetch all the submodules dependencies. Then you would have to run some make commands. But also very important is that if you choose to install it, please be sure to have all the system dependencies pre-installed before, or to install them first, because without them you wouldn't be able to run the make commands. Okay, so let's look over a specification. As I said, first I'm going to show the Solidity code, which is some kind of ERC20 token, but it's not correct. It has some bugs in it. So don't trust it and don't use it for any one of your projects. But yeah, you can see it has balances, allowances, it has the total supply, decimals, a name and a symbol. It has a constructor to initiate all those values. We have some getters and some of the ERC20 functions like transfer, allowance, approve, and transfer from. Okay, so basically this is the contract. The next step would be to have a specification. As I said, we need to know what the contract should do. So for this example, we would look at a few functions. So the decimal and the total supply functions should return the correct storage slot, and they shouldn't do anything else to the state of the program. So they're not supposed to change anything in the program, just returning the correct value. Okay, and then we have the approve function, which should update the correct storage slot, should do nothing else. And if we look at the code, the approve function has two requirements. So if either the owner or the spender is the zero address, then it should revert and shouldn't continue executing. In the other case, in which the owner and the spender are not the zero address, then the allowance of the owner for a specific spender should be updated to a specific amount. So basically, this is what the approve function does. All right. So this is our specification. The next step would be to write the formal specification, the one in K. So here I'm just having some snippets of it, which I'm going to show you right now. So this is how K configuration looks like, which is representing the state of the Ethereum virtual machine. And it's made out of what we call cells. So for example, we have a cold data cell and the status code cell and so on. So here you can see that we're calling the decimals function, and in the K cell you can see that we want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish. We want to execute the entire program from start to finish that all of the executions, in all the cases, we want the status code to be a success. So we are not looking for reverts. We're expecting to program to succeed in all cases. Okay, and we also want the function to return in all the cases the decimals value, which is a symbolic value. And we can see here in the requirements down below that the decimals come from the account storage. So here we have the account, which is the contract, and we are doing a lookup inside its storage, looking at the decimals key, and we're taking that value and returning it. Also here in the first part of the operation, we're doing a bitwise operation because in the contract, in our contract, the decimals value is a uint8. So we're doing this bitwise operation just to take that specific 8 bytes. Okay. So that would be how a specification would be written. There should be other fields. For example, the specification also requires the program, the bytecode of the contract. So that would mean that you would first have to compile the bytecode with the Solidity compiler. Let me do it here. For some reason, it moves pretty slow, so this is the same contract, and I'm gonna use solc to compile it. So this would actually be the bytecode of the contract, the binary part, which is also the compilation of the Solidity. So from Solidity, which is a higher level language, go to the bytecode, which is the input of the Ethereum virtual machine. So each byte represents an opcode, and it's executed by the machine. So yeah, basically the next step would be to take this bytecode and put it into the specification, which I showed you snippets of, and then you would have to run the proof. So I already introduced the bytecode for the purpose of this presentation, and I'm just gonna run the prover. So I'm just gonna one second. Okay, so while the prover is working, it should take a while, a few minutes, because it's oh, actually, I'm gonna stop it now because I skipped a step. So yeah, here is the specification, and how does it actually look like. One other advantage of the K framework is that you can write it in Markdown, and the code snippets which are actually executable are inside the K annotation tag. So basically, you can store your code and add documentation. It can be pretty easy from this point of view. So yeah, most of this part is boilerplate. Like there are some things required, but here is our claim, which was also in the slide. So the first part of the cells are, as I said, boilerplate. We're not gonna look into them, but they are still required because without them, the prover would complain. All right, so since I have multiple claims here, I'm just gonna comment out the ones which I'm not talking about, and I'm gonna keep only the claim for the decimals function. Okay, so now I can execute it. Sorry for that. Yeah, so this is, as I said, the decimal function. For the total supply, it should be pretty similar because it's also a getter. So basically, you would just copy paste the decimals function as a starting point. You would have to adjust the call data cell to call the total supply function instead. And you will have to adjust the storage slot lookup in the requires clauses. So, for example, here, this is the claim for the total supply. And you can see that we are now calling total supply instead. We're also returning the total supply value. We are still expecting success in each execution. And we're getting the total supply value from the storage, and we're gonna look at the total supply position. So this value is actually, I think I'm gonna go back to the Solidity code and explain. So when a contract is compiled and is stored in the storage, each of its fields is gonna be at some kind of index. So for example, and there will be counted from 0. So for example, balances would be 0, allowances would be 1, total supply would be 2, and decimals would be 3, and so on. So basically, this is just sugaring the value. Okay, and as I said, another key feature in the claim is that the account storage stays the same, and that's how we verify. So, for example, here in the status code, you can see that in the beginning, there is a value. There might be a value, which the initial value and how the cell is initialized. We do not care what that value is, but we care that in the end state, we would have a success. So it's actually a rewrite. Here in the
Hi,
storage,
Andrea. Sorry for the interruption. There's a one question.
yeah.
It's like Mohammed is asking, the bytecode are the opcodes, so he's kind of confused about the relationship here.
Yeah, so actually the bytecode is the numerical representation of the opcodes. So I think I have the opcodes here, the bytecode here. So for example, if I take this bytecode and go on to a website and look for, I think Etherscan has a pretty good tool, Etherscan disassembler. So basically here you would introduce the bytecode which is returned by the compiler, and you would decode it and have all the opcodes here.
Great, awesome.
Yeah. Okay, so let's look back at the proof. Okay, so we can see that the process returned a sharp top, which in our prover means that everything is okay, the proof is complete, and we have the guarantee that the decimals function works as expected and works as a getter should work. And it has no suspicious WS code which would change the state. Yeah. So going back to the storage here, as I said, the account here is where we check that the account storage doesn't change at all. So the way the storage was in the initial state is the same way the storage is going to be in the final state. Okay. So far so good, because everything is pretty straightforward, because we only have one case. There's no breaking points. There are no branching points. But let's look at the approve function, which, if we look at the code again, sorry for all the going back and forth. So yeah, as I said, the approve function has initially 2 values, but it's gonna call an internal function, and we're actually gonna look. Actually, the internal function would do all the work. So if we're just gonna look at the internal function, as I said, it has the 2 require clauses, and if the values are good and these conditions are met, then the allowance of an owner to a specific spender would be updated. Yeah, so if any of these would fail, then we would go into a revert case, basically. So, okay. That means that we have 2 cases: the case in which the values provided, the arguments provided work, and the case in which the function would have to revert. And we must specify both of them because we care that the contract works as behaves as expected in both cases. So let's look at the specification here. So yeah, if we are looking at the success case, we can see that we are calling the approve function with 2 symbolic identifiers, 2 symbolic values, and as before, we are looking at the entire execution of the program because we have no interest in starting the function at midway. This time the function, instead of returning a value, only returns true or false if the function behaves correctly or reverts. So in this case, since it's the success case, we are also expecting that in each execution, the status code would be a success case. And okay. So in the contract storage, this time, we have a rewrite, meaning that the account storage should be the same as initially. The only difference and the only update would be that for the allowance key, which is the position in the storage or the index of the allowance of the owner to the spender, in that case, the amount is updated. So again, this is the successful case. So yeah, as requirements, you can see that we expect the owner and the spender to be in the range of an address. We're expecting the amount to be an integer, an EVM word, from which takes values, as I said, from 0 to 2 to the power of 256. And we're also expecting that both the owner and the spender are different than 0. So here is where we are doing the check. Okay, so with this proof, with only this specification, we would look at, if I go back to the symbolic execution diagram, we would only look at a single part of this space, because since we haven't tested the case in which the function fails, we are not looking at all the corner cases and all the space of the values. So that is why it's important to take all the corner cases in consideration. Okay. So the revert case is pretty similar, but with a few key differences. We're also calling up the approve function with the symbolic values. This time we don't care about the output, so this is what this underscore means here. But at the status code, it says that we're always expecting a revert. The storage shouldn't change. And as a requirement, either the owner or the spender, one of them should be equal to 0. Yeah, and this should result in an EVMC revert always. Yeah, so basically this is how this is our approach to formal verification. Yeah, also what I wanted to say is that, for example, if you choose to, or you don't take into consideration all the cases, and for example, you forget to put these constraints. So for example, if you delete it or comment it, then the prover would throw out some error messages and throw out the configuration of the a configuration of the state in which the prover stopped. So I also did that before, and this is the configuration for the case in which we are doing the success case, but without the requirement that owner and the spender should be different than 0. So in the case in which they are commented, for example. Okay, so in that case, I know it's pretty big and pretty ugly, so I'm just gonna go through some key cells and explain them. So the key cell, which always shows the execution or the instruction at which the machine is, it's at hold. So since it's the same as in the specification, it means that the function executed completely and we're at the final state of the machine. Okay, so in the output cell, without the padding of the bytes, we can see that we have the message that the proof was from the 0 address, and we have a revert case in the status code. So the function reverted. Okay. If we also look at bottom at the requirement clauses, or where requirement clauses should be, we can see that the owner at line 100, we can say that the owner equals 0. So basically it showed us the case in which, or a counterexample in which the program failed, where the proof failed. So basically from this point, if I was writing this specification, I would look at the Solidity code, look why the program fails when the owner is 0. I would see the requirement clauses, and then I would update my specification to add the clause which I just uncommented, or I just commented. So yeah, basically this is how we do verification. Okay, so yeah, that's most of the presentation. I would also like to tell you that we have a tutorial for the K framework, which takes you from 0, from installing it, and it goes to all the way to proofs, which I talked about and presented you now. So if you want to learn K and it's appealing to you and you want to try it, you can try this tutorial. Okay. We also have, we are hiring. We are looking for a full stack developer and a technical writer to help us with the blog posts. The full stack developer should have knowings of Python and React.js. But if you want to try, send us your resume and we're gonna respond. And yeah, we have a Discord channel and a newsletter. If you have any kinds of questions about the K framework or the K EVM, then drop a question there. We will answer pretty shortly. So yeah, any questions or?
I guess not any question from the viewer side, but yes, would be great if you can share those links. Yeah, it has already been mentioned in your slides as well. I can see, but would be great if we can share those live, right? To learn K frameworks and all.
Okay, should
Mhm.
I share them in the chat here
Yes,
or?
yes, you can just share in the private chat, and we can just forward it.
Okay, sure, I will do that. Uh, Let me turn off the share screen. Yeah, so
Got it. Uh,
I'm gonna send all the links now.
mhm. Got it. Let me just quickly forward it down. Right. Yes. So yeah, Gene is saying great talk, and he's actually thanking you for the presentation. So yeah, I can say like what do you think, Andre? What is the world around formal verification like? Is it uh like that much wide regarding normal auditing that we have, or what do you think, like it's still being unexplored, and we have a lot to do in formal verification, or it's still not being followed at a you can say a wider scale?
Yeah, so it's not so widely adopted now, so there's
Hmm.
a pretty huge opportunity for everyone to join in. Um, but yeah,
Okay, so
mm,
what is our approach that you would recommend for a person looking forward to learn or get into formal verification? So I guess KVM is one thing that one should be looking forward. Like, what would
uh,
you recommend?
okay, so KVM is our approach, but it's not the only formal verification tool out there. I know there are,
Mm-hmm,
from top of my head, there are very fast and Otter.
mm-hmm,
There's also an HEVM, an implementation of EVM in Haskell.
mm-hmm,
So yeah, but in this time where everything or most of the information is on the internet, I'd say that it would be interesting to start learning and looking at a bunch of papers. Like I know
mm-hmm,
there are some papers out there online.
mm-hmm,
Um, so I'd say yeah, that's one way to do it.
mm-hmm. Yeah, please let me know those papers so that I can just attach it with your slides, and I will just forward it down into the channel. And yes, I'm just waiting for some questions if we have from the viewers, because yes, we know formal verification is still a very new space for everyone to jump into. But yes, I hope if we get more questions, else we are good to go. Let's just give 5 more minutes.
Yeah,
Mhm.
sure.
I guess we are not having any other question. So I guess with that note, we can actually end the day one. So it was amazing, and ending it with formal verification just added a charm to it. So yeah, thanks Andre for coming up and joining Unchained. So like again, we can just say thanks to you for being a part.
Yeah.
Completely our honor. And yeah, looking for more such events and more such collaborations with you.
Yeah.
And yeah, with that, I will just want to say best of luck for all the runtime verification team, and just keep rocking.
Yeah. Thank you for inviting me. So
Yeah.
have a nice day.
Thank you, Andre. Have a nice day. Bye bye. See ya. All right, Arnab, hop in.
Hey, visible, right?
Yes, you are completely visible. Where is your coffee, man? Right,
So,
I just had mine. I just had mine, coffee and all. So yeah, completely prepared. And yeah, end of day one.
yeah,
It was nice. It was nice, and so many good things. I actually personally learned, and hopefully viewers as well, coming from different time zones. I know it would be like it was a pretty difficult task, but yes, thanks to all the speakers who, irrespective of the time zones, joined us and shared the valuable research and knowledge. And yes, what do you want to say on him?
yeah. I mean, as a closing note, I would definitely like to thanks every speaker, every participant
Hmm.
who have been continuously on our journey to educate
Hmm.
the community and
Right.
have been following along since
Hmm.
the morning. Like we have
Hmm.
been almost we have
Right,
been.
and I want to actually thanks the constant viewers that we have.
Yeah,
Mohammed is the one. He's like watching from like from the very first talk. He's constantly connected and constantly asking questions. So yeah, I just want to thank him like for the wonderful support giving us. And yes, he's a very amazing guy. So yes, with that, we have other members as well. We have Gene, we have Davis. I remembered, and yeah, there's one more guy who has actually no username, so I don't know how to actually call him. Yes, so we have a lot more members. I just want to name them. Uh, which have actually given us a tremendous support throughout the session. Yes, and yeah, I guess yeah. So yes, these were live throughout our event and constantly supported us. So but yes, still we are not done yet. We are not
yeah,
done yet. We have one more day, and we have a couple more speakers. We have Mudit Gupta with us, um, the man himself. Like whenever we get a post from him, yeah, we get vibes like, oh, we know somebody somewhere got hacked, got wrecked
yeah.
somehow. Yes, so so that's one thing. And who
And
did
of
we
course,
have? So let me just check
your,
the
yeah,
let me just check the schedule once. So next time we have Josh. Yes, Josh is like again another, I can say, a very crazy person. Like I don't know if anyone is following him on the Instagram or not. You name it, he's probably doing it. Any you can say a sport you have in your mind, he probably does that. Like skating, BMXing, and what else? I don't know. Jutsu,
it,
yeah, jutsu as well, and chain tooths for tutorials and like whatsoever. And who else? Yeah, Mudit is there, and yeah, Sleepy will be coming with us. So he's again like pretty active guy on the Twitter and shares valuable information. And then we have Timur. Yes, Timur will be talking over Rust. So we actually requested him to join into Unchained and share some knowledge around Rust, because yes, we probably talk just about Solidity and just probably about Ethereum and smart contracts, but the thing which is still being lagged upon is the Rust. And yes, we need that information and we want to learn that as well. And we have Rex as well, who will be coming up with a uh, new topic, you can say, new solution that his team is basically building a kind of a scoring system for smart contracts, and based on the risk analysis that is related to a smart contract. Because giving an example, we have some very popular token, and anyone just can go ahead and fork that token and make their own well-known like make a fork of the token. Like let's take an example of USDC, right? I can just go ahead and copy that code and make my own USDC. And for a non-technical perspective, like from a user's perspective who don't have enough knowledge, like to go ahead and figure out which one is the real one, as it's like it's pretty much uh less information available. Like you are supposed to have that technical and sound knowledge about that. Otherwise you will fall into a prey of rug pulls, scams, and whatsoever. So with that, they are trying to build some solutions. And yes, if we have another day and some cool new talks. So with that, so this is my ending note, and over to you, Arnim. Please add your points, and then we can wrap up.
Yeah,
Yep.
like so first of all, thank you very much everyone who has been continuously watching our live stream throughout the day. I mean, we just started in the morning and it's almost night here, and
Right.
we're going to wrap up real soon. So thanks everyone, and just stay tuned for tomorrow. Like tomorrow's second day would be the last, the final day for Unchained, and we like as Jason already mentioned, we are going to have a lot of speakers who
Right.
have contributed significantly in the industry. Like everyone has, but still. So just stay tuned. Like this year edition is going to be a really
Right.
uh,
Yeah, the talks are going crazy, man. It started with blockchain, moved on to hyperledger security, then came down to formal verification. I don't know, like we have probably covered like all the needed components, we can say, uh, in the security space of Web3. On a decentralized world, we got some tools as well. Uh, Mohammed pointed out like how to make a cloud environment around Slither. Uh, Yoran was there, pointed out Scribble and property testing, and yes, so the things are going crazy. And yes, with this event, we all are just learning, and we want more such events and more such community support. And just keep rocking, guys. Keep hacking. With that, I guess it's time to say goodbye for the day one. Day one, not for the event.
yeah.
And yes, what a great day! Thanks for you. Thanks to you, Jing, for joining and constantly supporting us. And with that, we can say goodbye, Arnim, to the day one.
Bye.
And bye bye,
Catch you
everyone.
tomorrow.
We'll see you
Bye.
tomorrow. And have a great day. And keep like stay in security and keep hacking and be a white hat. That's I want to say. Don't be on the attacker side, right? I know flash loans are very much productive and can yield some good amount, but yes, we want more white hats. So be on the white hat side. And see you soon. Have a great day. Bye bye.
Bye.